Okay, hi everyone. Welcome to this short course on Introduction to Quantum Repeaters. And Prateek and I are going to deliver this course. Filip Rozpedek, who is also faculty at UMass Amherst, has helped uh, also to create this course. Um, so let me begin just by sort of welcoming all of you and thanking you for for taking the time to join us. And I hope that you get something out of this course. This course kind of sits in the middle of a few courses in this winter school. For example, you have the level 1, 2 courses on uh, just a general introduction of quantum networks and how things work on a high level. Then you have very focused courses on, say, things like the information stored in a photon. You have courses about the quantum memories specifically, uh, the hardware requirements, and then how things are fabricated and so on. So this is a wide range of topics that is going to be covered. We are sitting somewhere in the middle in the sense that you will see a little bit of the physical picture in this course as well. So we'll talk a little bit about memories. We won't go too deep into it, but we'll tell you hopefully enough for you to get a sense of how architectures work, and then we'll go to architectures as well. So therefore, that's why I say that it kind of sits in the middle. And then, as was mentioned, we will take questions in the form of in the chat box, and both Prateek and I will be monitoring it. So feel free to put in any questions that you have there. All right, so let's begin then. As I said, the outline, we have 5 parts in this course. I'll deliver the part one first, and then Prateek will talk about the operational primitives and the architectures, and then we will go on to the architecture level discussions about all photonic repeaters, and we'll try to do some kind of performance comparison. Okay, so before without further ado, let me actually go into the core part of the talk. So let's see. So let's try to motivate a little bit why one needs quantum repeaters. I guess since you are sitting in this course, you probably are motivated why we need quantum networks. And as you might have seen in other courses, but even if you haven't, the idea is that information, the task of carrying information in quantum networks is primarily uh, given to a photon, because that's your flying qubit. And when you are trying to use a photon for communication and you are trying to preserve the quantum degrees of freedom of the photon, then directly transmitting the photon from a distance from a point A to point B, if the distance is too large, leads to exponential losses. And that happens in the classical case as well. But in the classical case, because there is no restriction from the no cloning theorem and so on, you can always amplify your signal and get back the stuff. Whereas in the quantum world, you cannot simply amplify your signal. Therefore, this is a much bigger problem in the quantum world, that you have exponential loss. Now, the physical model behind that is simply the absorption, right, of the photons whenever it passes some medium. This could be uh, the atmospheric medium. This could be a fiber optic cable. Uh, this could even be sort of a simple glass, right? But ultimately, as the photon moves through the medium, it has a high probability of getting absorbed. This, in technical terms, is also sort represented sometimes by this very famous plop bound, which tells you what is the maximum secret key rate, which is a figure of merit for how good your quantum communication is, how much quantum communication can you do through the channel, what is the upper bound that you can have on that if you have a transmissivity of eta. And the transmissivity is simply the probability that you will reach from A to B when you are going through a channel, right? And you can see that that falls logarithmically with decreasing eta. So as you get more and more loss, at some point your key rate is just going to go to zero very quickly. So direct transmission is not an option beyond, say, 10, 20, 30, 40 kilometers, right? So definitely not for metropolitan scales. Now, again, to quantify that a little bit more, you can think of the probability of survival of a photon when it's traveling through a channel, which is of length L, as this number. So you see that it falls exponentially with increasing length. And there's a coefficient here sitting, which is the attenuation length of the medium or the channel. And this is usually for fiber optic cables, this will lie somewhere between 10 and 20 kilometers. Right? And therefore, you see that idea that directly, if you wanted to communicate, probably 10, 20 kilometers. Now, if you see the inverse of that quantity, so if you were, say, for example, trying to share an entangled photon pair between points A and B, and you had a source in the middle, right? So this is some source which produces a pair of entangled photons, right? And your aim is that A and B should get that pair, right? So both the photon from the left and the photon from the right should survive. Each of them has to pass through a length L over 2. So you see that the probability of survival being P, the amount of time that it will take on average for you to share successfully a pair, as in both of the photons from the same pair reach A and B, is roughly equal to this quantity. So you see that time also increases exponentially now with increasing L, right? So that's a problem. Now, what you should then think of is, I'm sorry, here I think there is a typo here. This should not be minus; it's a plus sign. So you see that the waiting time actually increases exponentially. Now, one solution to this problem is that you can say, okay, maybe I can't go through the whole distance L. Maybe I should divide it into parts, right? So say you decided to divide it into two parts, right? In which case, the probability for each section will increase quadratically, right? So if in principle you could do these both of these link generations as they are called, or essentially like sharing an entangled link in the first part and sharing another entangled link in the second part, if you could do them simultaneously, if you can do them in parallel, then to some extent your task is done still, right? You still have to think a little bit more beyond that, but at least that seems like to be a solution, right? Now, if you divide it again into n parts, then you will see, in fact, and it's straightforward to see that the probability of survival will increase exponentially for each segment, and therefore the waiting time for the direct communication will be exponentially larger for the communication based on this divided segments. Right? So the divided segments will allow you to reduce the waiting time by an exponential factor n, where n is the number of segments that you have decided to divide this. But this is, of course, not the end of the story. This is the beginning of the story, in the sense that, okay, I say that I divide them, but my aim ultimately was to share a photon entangled pair between A and B, which was the two ends, and not just between the segments individually. So the way to do that is by somehow, first of all, guaranteeing that all of these things can be generated in parallel, right? There's some kind of synchronicity that you can achieve in the generation of all of these things. And then once you have these individual sections, how do you join them together? How do you glue them together? And this is where a quantum repeater comes in. So what a quantum repeater allows you to do is to generate these links in parallel, or to do all of these operations in parallel. And once you have that, it allows you also to glue these smaller entangled links together to get a end-to-end entangled state. And this is roughly the motivation for why one would want to use quantum repeaters. All right, so a quick poll question now. What kind of improvement in rate can we get by using quantum repeaters over direct transmission in the ideal case? So you can have quadratic, exponential, no improvement, or performance actually goes worse. So I'll wait for like 30 seconds for you to put in the poll answers. So I see. Okay, wonderful. So most people think it's exponential. Good. A few people think it's quadratic. Not to so everyone more or less thinks that there is some improvement. And yes, so the right answer is that you get exponential improvement. And again, mind you that this is in the ideal world. If everything worked perfectly with your quantum repeaters, that's what you can get. But of course, it's going to be a more complicated question. For people who put in quadratic, you are also partly right. If you only had two segments, then it would be a quadratic benefit. But if you had n segments, it kind of grows exponentially. All right. So let's now, after we have motivated why we need quantum repeaters, let's look at a little bit on the physical side of things and see what physical principle or primitives allow you to do this to implement this repeater. And the key idea throughout this part will essentially be that photons are very good carriers of information. They travel fast, they can travel far. and they have a lot of degrees of freedom, so you can store quantum information in them, but they are always flying, right? It's very hard to stop them or to slow them. There's an entire field of physics, it's like on slow light and so on that works with that. And this is essentially what you want to do in some sense. So you want to slow or you want to stop that photon. And one of the ways to do it is to store that photon's degree of freedom into some kind of atomic system in form of the excitation of the atomic system. So let's see. So one of the essential elements of a quantum repeater is what is called a quantum memory. You will hear a lot more about this if you go to, or if you have already gone to the quantum memories intro to quantum memories course in this winter school. But let me give you sort of a high level picture of how these memories work. So memories essentially, as I said, their task is to store the flying quantum information in the form of some collective excitation, right? And you can have two kinds of memories, broadly speaking. And there are many technologies that sort of fall into either criteria or both in some sense also. Uh, but but one of the broad classes is what is called an absorptive memory, where you see what is going to happen is you have some kind of atomic system. Usually these are what are called lambda systems, where you have two ground states which are relatively stable and long lived, and there is some kind of excited state into which you can couple the ground states to, right? So you can move the electron up and down, and or the entire atomic state up and down, depending on what system you have. But essentially, the idea is that the photon is coming in, and it moves into this medium, which has these atoms, right? And then you send in a control pulse. So you see on the figure in the bottom, you send in a control pulse along with the input signal, which is in blue. And what it does, it kind of makes the medium absorptive for that time period, right? So as the medium sees the control signal, it realizes that I need to take in the photon and transfer that into some kind of excitation of the system. Then it stores it for some time, right? So this is the main task of the quantum memory. It takes in the input signal, stores it for a while, and then if you send another control pulse, the other one, then you can bring out the photon. So the atomic excitation now converts back to the photon and it comes out, right? So the quantum information can both be uh, caught inside the atom, and then on demand you can also take it out, right? And that is essential. If it was only one way, then it would be more difficult to do a lot of quantum photon. So this is about absorptive type memories broadly, and there are many examples: electromagnetically induced transparency-based atomic vapors. Then you have what is called atomic frequency comb, and each of them has kind of a different way of achieving this protocol, but it's roughly the same idea. The other broad class is what are called emissive type memory. So instead of saying that I have some entangled photon already, or a part of an entangled photon already that I'm trying to absorb, let's try to create a photon which is already entangled with an atom, right? And then let's see, can we create entanglement between the atoms using that? So this is how an emissive memory actually works. So you start with again a lambda-like system, right? You have two long-lived ground states, and you have some excited state E, right? And when you say you first create a kind of superposition state of 0 and 1, and then you send in a control pulse again, right? What it does, it excites the atom, right? So the atom goes to this excited state E. And the key part now is that once it decays back, because it's an excited level, and these ground state levels are more stable, it's going to come back at some point, right? And once it decays, depending on what state the atom decays to, you get a photon with a different property, right? So this could be, say, for example, the color of the photon, that's frequency of the photon, right? So if it goes to 0, this could be a red photon. If it goes to 1, it could be a blue photon. Now, of course, these are sort of uh, just an example. Things will be more subtle, but this could be polarization, this could be temporal differences, so on, right? But some degree of freedom would be different. And essentially what this allows you then is to say that if I don't know which part the which state the photon decayed to or the atom decayed to, I also don't know the color of the photon emitted, right? But what I can say with surety is that if the photon was of color red, then the atom must have decayed in the state zero, right? So you can say that with some probability mod of alpha square, the atom is at the state zero and the photon emitted is red color. Whereas with some probability mod of beta square, you can say that is the other way, right? That the atom actually decayed to state one and the photon emitted was blue, right? So what you end up is with a highly correlated state of the atom and the photon, or an entangled state between an atom and the photon, right? So the atom photon state is an entangled state now. Now that's part of the job done. I want some way to entangle two far apart people, right? This is just the photon coming out of the atom, which is entangled, and now the photon can move far away, right? Now, if you have two such systems, one on the left and one on the right, as you see in this figure, A and B, and each of them is emitting a photon, which is entangled to A on the left photon, and then on the right photon is entangled to B, and then you merge them or you interfere them at a beam splitter, right? What a beam splitter does essentially, and this is a 50-50 beam splitter, say for example, it erases the witch path information, right? So once you detect two photons, one in D1 and D2 detectors, you don't know from which side which photon came from, right? So therefore, you kind of transfer the correlations that were there between Alice and the photon and Bob and the photon to correlations between Alice and Bob. And you see that if you sort of do the beam splitter math, you will see that the state that comes out after this operation is an entangled state between the two memories A and B, which is alpha 01 plus beta 10. And this is, as Prateek will also talk about this in detail, this is falls in this broad class of Bell states that are extremely useful for quantum operations. All right. So that's about the two kinds of quantum memories, right? So that's one part of your repeater that you can take the flying information in the form of a photon and then convert it into some kind of stationary qubit, or you can generate somehow entanglement between two stationary qubits. So another quick poll question. What key property allows the atom photon entanglement in emissive memory? So remember, we are talking about the atom photon entanglement. And the options are creating superposition states at the memory. Property of the emitted photon depends on which state the atom decays to, the excited atom decays to. Interference of the photons at beam splitter, and collective excitation of atoms when photon is absorbed. So we are talking about emissive memories and we are talking about atom photon entanglement. Okay. So the majority of people said property of the emitted photon depends on which state the excited atom decays to. That's absolutely right. Yes, the superposition of the memory initially also helps in generating the atom photon entanglement, but the key property really is this kind of dependent emission, right? So that's B is the correct answer. Okay. So now that we have stored the quantum information, let's try to manipulate it, right? Because any kind of quantum protocol, you just don't want to sit with some fixed state, right? You want to do something with it. So there are these kind of two broad things that you need to do, but before that, let me just briefly take a tangential and talk a little bit about the Bloch square representation, pure states and mixed states. So if you have a single qubit, a very nice way of representing it is through a Bloch sphere, where the different coefficients of the state can be represented as the two angles and the position of the and the length of the vector on a sphere, right? So essentially, you can take a quantum state and write it in some spherical polar coordinates, right? And for example, in this kind of nice representation, all the pure states or all the states where you have no classical mixing, everything is quantum, lie on the surface of the sphere, right? If you have a single qubit, everything lies on the surface of the sphere, right? For example, the states 0 and 1 are living on the north and the south poles, right? The plus and the minus states, which are the x eigenbases, right? They live on the equator. Similarly, the y eigenstates also live on the equator. So this is a nice way to represent these things. And then if you have a mixed state, which is essentially a classical mixture of quantum states that, say, for example, in a box, you have 100 states, 50 of them are zero and 50 of them are one, right? And now you pick up a state at random from the box, right? You have a 50% probability that the state is zero, you have a 50% probability that the state is one, right? But it's not a 0 plus 1 pure state, right? It's not a superposition of 0 and 1, it's a mixture of the states 0 and 1. And those kinds of states actually live inside the block sphere. So if you see anything that is sort of squished in, right? Or if you take a state and you see that by doing some quantum operations, the state actually squishes in and it gets inside the block sphere, you realize immediately that some kind of non-unitary operation is happening, and you're losing some information, and the state is becoming from pure, it is becoming more mixed. And the maximally mixed state actually lives at the center of the sphere. For example, the 0 0 plus 1 1 state that we were talking about, I mean, the zero out product zero, one out product one, maximally mixed state actually lives at the center of the block sphere. So that's about pure and mixed states. And then another key point that I would like to highlight at this point is the idea of the density matrix, right? So what you can do on the block sphere, you can also write it the same kind of single qubit state as a 2 by 2 density matrix. And when you do that, so this is just another way of writing. The diagonal elements tell you the ratio of the populations, right? So this is the classical mixing part that I was talking about, right? That in the bag you have some zeros and you have some ones, and you pick out at random what is the probability that you have zeros and what is the probability that you have ones is given by the diagonal. But if apart from that mixing, each of the state that you pick up, or amongst the states, there is some kind of superposition that's also happening, right? So for example, when you picked up things, it was not just the 0 or 1 state, it could also be the plus state, right? Where you have some superposition between 0 and 1. That is actually represented by the off-diagonal elements of the density matrix. So remember, whenever you see a density matrix for a single qubit, or even for multiple qubits, the idea is that if you look at the off-diagonal elements and you see that they are shrinking or they are not there, you know immediately that this is a more classical state, and it has lost coherence, it has lost superposition, which is the essential quantum property. All right. So how do we do single qubit operations? Now, with that knowledge about block spheres and pure states and mixed states, the idea is that you have some pure state, right? So it lives somewhere on the surface of the sphere, and you want to bring it to another point on the surface of the sphere, right? So you want to have your quantumness retained, but you just want to turn around the state, or you want to just rotate the state on the sphere, right? So essentially, this is how a single qubit operation occurs. Every single qubit operation is essentially rotating your qubit on this block sphere, right? And the way to do this is, if you have the states, say 0 and 1 as your basis states, and there is some kind of coupling between them, you send in a control pulse, which is a laser, a radio frequency, microwave, whatever, right? And depending on the duration of this pulse, right, this electromagnetic wave that you are sending into the system, and the strength of the pulse, right, these internal states, 0 and 1, will mix amongst each other, right? And that will allow you to rotate the state from whatever point on the block sphere to some other point on the block sphere. So the strength and the duration of the pulse is what tells you how much you will rotate, what direction you will rotate along, right? That will allow you to do a single qubit operation. So that's sort of a high level picture of how single qubit operations work. For example, here you see the zero state is rotated by angle pi through a pi pulse, and you get to the state one. Now, how do you do 2 qubit gates, right? Because 1 qubit operations are not enough to generate entanglement. So if you had 2 qubits and you just kept doing single qubit operations on them individually, there would not be any entanglement. What you need for entanglement is some kind of interaction between the qubits, right? So the idea then also is that, okay, if there is some interaction between the 2 qubits, but it's always present, right? So if I have, say, 5 qubits in my system and they keep interacting all the time, right? Then also it's not ideal, because what it tells me is that there is no way to individually control the qubits, right? All of them keep getting mingled up together all the time, and I cannot do individual operations on each of them. If I do something to one, something happens to the other. So that's also not ideal. So I should have some interaction between the qubits, but I should also be able to switch on and off that interaction, right? I should be able to make it, at least make it strong and weak, depending on what I want. Now, this interaction can either be a direct coupling between the qubits. So you can have, maybe, as we saw in the lambda system, right? Through the excited state, you have some coupling between 0 and 1 already existing, right? Or between the 0 and the excited state, there is already a coupling. If you send in a control pulse, the photon gets excited, right? And the switching on and off can be through this laser or this microwave field, right? So that's your control, right? And if that is allowed, then you can have some interaction between the two qubits A and B, and that lets you do a 2-qubit gate. And there are many examples of what those interactions can be. These can be hyperfine couplings, like the magnetic field induced couplings and so on, or dipole interactions. But essentially, this is some kind of dipole, which is controllable through a field. Or you could have an indirect coupling, right? And this is very common, for example, in ion traps, right? Where it's not that the ions, if all of them are sitting in the trap, it's not that they directly couple to each other. They couple to each other through what are the electronic modes don't couple to each other directly. They couple through what is called the phononic modes, or the vibrations of the ions, right? So what you can have is that, okay, qubit A and B, they don't talk to each other directly, but I can switch on an interaction between the qubit A and some kind of bus, right? Which is essentially, for example, these phonons, right? Some other excitations, right? I can switch on that coupling, and then when I want to do an interaction between A and B, I switch on the coupling between B and the bus, and that essentially does a AB coupling or an AB interaction. So those are the two primary ways. You can either have direct coupling or you can have indirect coupling, but you need interaction. Okay, third poll question. When using the block sphere representation, where would a mixed state reside? A at the poles, B at the equator, C some point at the surface of the block sphere, D inside the block sphere. So remember, again, try to remember, where do pure states live and where do mixed states live? And what do you see when you go from a pure to a mixed state? All right, let's see. Okay, so majority said inside the block sphere. That's the right answer. Some people said at the equator, some point at the surface. So at some point at the surface of the block sphere, there would be states, but those are pure states, right? So that's what you have on the surface, and then at the equator also you would have the pure states, for example, the plus minus states. The correct answer is inside the block sphere for mixed states. Okay, so now that we have stored the information in the memory, inside the repeater. We have learned how to do some kind of operations. Now let's get real in some sense, right? So, okay, all of this is very nice, but everything that you do will be error prone, right? Because you cannot, first of all, store that quantum information perfectly. Once you are storing, there will be errors. Once you store it inside, as time goes on, the system will interact with other systems in the environment, and you will have loss of quality of the stored information, because it will get entangled with other things in the environment. And then once you try to do these single qubit and 2-qubit operations, there will be more errors, right? Because these control pulses, for example, that you said, are never going to be perfect, right? They're going to be a little off in the area. They're going to be a little off in the duration and the strength and so on. And the couplings will also not be exactly what you sort of theorize, right? So everything that you do with a quantum repeater is error prone. And we should know what those errors are, or at least we should have some kind of models, simple models, to deal with them or to account for them when we are assessing the performance of our architectures, right? So the first kind of error is essential when you look at a quantum memory, or when you think about a quantum memory, is the storage noise, right? So once you store quantum information in a quantum memory, it's not as if the information is stationary perfectly, right? We say that, okay, you have moved from a flying photon to a stationary qubit, but qubit is not really stationary. It's constantly interacting with the environment and it's moving on the block sphere, right? It's constantly moving on the block sphere, it gets inside the block sphere and so on. Of course, if it's moving just on the block sphere, you can always rotate back, so that's not a big problem. But what really is the problem is if you lose coherence, right? So if you lose coherence, the block sphere shrinks and you get inside the block sphere, you lose your quantum properties. So one of the most standard models to look at storage noise in quantum memories or decoherence in quantum memories is what is called the T1 T2 model, where T1 essentially tells you about the loss of population from 1 to 0, right? So if you were trying to create a superposition between 0 and 1, right? So let's say you created a plus state, right? So now if one of the states is of a higher energy than the other, right? So say 1 is an excited state and 0 is the ground state. You will have a tendency in the atom to decay back, to fall back to 0, just spontaneously, right? So you don't have to send a control pulse, it will have its own tendency to fall back. And what it does to your density matrix is that it reduces the one state population, as you would expect. It increases the zero state population, as you would expect. But what is worse is if you started with a plus state, remember it's an equal superposition of 0 and 1. But if you now start losing photons from 1 to 0, that superposition also starts vanishing. And you see that by looking at the off-diagonal elements, and you see immediately that they also fall exponentially by and the strength of that fall is dictated by this parameter T1, which is called the relaxation time or the T1 time of the memory, right? So that's one way in which you lose coherence. And then the other way is directly by this kind of random rotations, right? So remember, if you have a simple rotation on the block sphere, then you go from a pure state to a pure state. So there's no problem. But if this rotation is random, you don't know how much your atom has rotated, or the states have rotated, or the qubit has rotated. You don't have a way to completely determine the state, right? So therefore you lose information and you become a mixed state. And that's what you see, that in this case, essentially what happens is that the diagonal elements are still the same, right? Because you're just rotating, right? So it's not that 0 and 1 populations are changing, but the off diagonal elements are changing because the amount of the amount of superposition between 0 and 1 is changing. So that decays very sharply with the scale factor T2, and that's called what is called the dephasing noise, right? Or the dephasing channel noise. So that's about storage, right? Now, if you wanted to look at more errors, right? So as we said, when the photon comes in, there is some error during absorption. When you do operations, there is more error. A very general model to look at is essentially what is called a Pauli model, right? For noise. Here, what happens is that you have these sort of 4 things that can happen to your state. So you start with some density matrix rho. It can either just go back to the same state with some probability 1 minus px minus py minus pz, right? So it goes back to the same state, no problems. This is wonderful. With some probability px, it can bit flip, right? So the zeros can go to 1 and the ones can go to zeros. So that's, if you remember, this is like the relaxation error, almost like the relaxation error, right? 0 goes to, at least this part of 1 going to 0 is like the relaxation. So part of it kind of also captures that. Then py is also similar to a bit flip, but here, apart from a bit flip, you also have a sign change. So that's a kind of a mixture of the 2 things. And then pz, as we discussed, is the phase flip, right? Or this is the T2, this is the dephasing, right? That the relative phase between 0 and 1. So for example, this is what happens for a plus state. So if you have a 0 plus 1 state, what a phase flip does is it takes you to 0 minus 1 state, right? And if you have a 0 minus 1, it takes you to a 0 plus 1 state. So it changes the phase. So so therefore it directly impacts your off diagonal elements of the density matrix, right? So this is what the dephasing part of the memory noise could be included in this. So all of these 3 combined together are the errors, px, py, and pz, right? And this captures a broad class of operational errors, storage errors, and so on for quantum repeaters, right? So this is a very, very good model to have. And then depending depending on what hardware you have, what different noise models you have, all of that can be parameterized into px, py, and pz, and you get a very nice sort of modular noise for modeling. Right? All right. So now that we have these noise models, let's also look at how would you look at a quantum memory? What figure of merits should you look at when you are judging a quantum memory, right? Whether it's good, whether it's bad, right? So one of the first things that you should look at, and that's where we started from, is the loss of coherence, right? How fast does the coherence get lost once you have transferred your photon to the quantum memory? How long can it store it? Okay. And that essentially is again, if you go back to the density matrix picture, it's the off-diagonal elements that you have to look at. How fast do they decay, right? And if you remember from the T1, T2 model, it's not just T2 which changes the off-diagonal elements, it changes them directly. That's absolutely true. So that's this T2 pure. But the T1 noise, which just changes from 0 to 1, just flips between, that just relaxes from 1 to 0, that also changes the off-diagonal elements because of this population change, right? And it turns out, if you do this carefully, that effect is twice as large as the effect of the direct phase flip. And if you want to look at the T2 time for a memory, right? So these are the numbers that are often quoted in literature, that what is the coherence time of this quantum memory? That's this T2 number. That will include, in general, always contributions from the relaxation and from this dephasing noise that we had in the because of the phase flips, right? So both of them put together, the sum is the T2 time of the memory. All right, but that's one part of the story, right? Because although you have this memory which can store information for a very long amount of time, you should also ask the following question: that this is a number which is often sort of swept under the rug, or gets unnoticed or goes unnoticed, is the efficiency of the quantum memory itself, right? That, okay, let's say you have this absorptive memory, right? Once the photon is in and it's stored, maybe it can go on for a long time, right? Maybe you can keep it for 1 second. But how much of the photon or how much of the information actually gets absorbed? That's something that you have to also ask, because if you send a million photons and only one of them gets absorbed, then that's not also a very good memory, right? Even if it can keep that information for an hour, right? So the goal with absorptive memories, as we said, is to capture an incoming photon. So the efficiency factor here would depend on two individual factors. One of them is what is called the absorption efficiency, right? Which is essentially, okay, just think of, if I send 100 photons, how many of them actually get inside the memory, right? And then there's another factor which is called the storage efficiency, which tells you, okay, it's inside, it's coupled to the memory now, but I still have to convert my information which is stored in the photonic degree of freedom to some atomic level, right? So there is some transition from one degree of freedom to another, and that transfer also leads to some loss, right? So there also you have to think about what is the efficiency of that process of converting the photon to some kind of, say, a collective excitation, right? And both of them put together give you this total efficiency of the memory. So if somebody says the memory efficiency is 1%, that tells you essentially that if you have 100 photons, one photon gets perfectly transferred to the quantum memory. And then you say, okay, what's the T2 time? How long can it keep it? And finally, then for emissive memories, also you can quantify this same thing, right? So you can say that, okay, now I have a atom which is emitting a photon, which is entangled with the atom, right? You will typically want the output photon to be of a single frequency or of a single mode, right? Because if it has like a huge bandwidth, then that's also difficult, because then you don't know how to make it interact with other other photons, how to get it absorbed in the next memory, and so on. So it should have some kind of fixed bandwidth in some sense, right? So when you have this emission from the atom, you send it the control pulse, and the photon is emitted, which is entangled with the atom. It's not that you get a single frequency out, or a single mode out. A part of that excitation is in this useful mode that you want, and a lot of it is lost in what are called these sidebands, right? So maybe this is just thermal excitation of the system itself. Maybe it's some other photons, right? All of that is not useful. So the fraction of the emission that is in the relevant mode is quantified by what is called this Debye-Waller factor, right? And that's this eta factor that you have here. And then, okay, the photon has come out. You still need to, again, you need to capture it, right? You need to couple it to, say, some fiber. Because remember, for example, when we were trying to create that entangled state, once this photon comes out, it has to go through some channel and meet at a beam splitter. If you lose the photon after it comes out of the atom, it's still not useful, right? So you use some kind of objective lens to kind of focus the output. Because remember, this emission of the photon from the memory doesn't have to be in a particular direction always, right? So it has to be coupled to some fiber, and there you also have what is called loss in collection, and that is quantified by what is called this collection efficiency. Right? And both of these things put together give you the total efficiency of a emissive memory. There are many other factors for both emissive and absorptive memories, but I have kind of tried to give you the main two types, right? So that's about the figures of merit. You had how long can the information be stored reliably in the quantum memory, and then how much of the information actually gets stored when you send it in. All right. I see that maybe okay. So I am done with my part, and then I'll hand over to Prateek. But are there any questions in the chat? I saw one.
I think there is a question on T2 and T2 star if you'd want to add more details.
Uh, yeah, I could. I don't really want to go into that detail too much, because you see, I mean, there's the T2 star idea is based on what is called dynamical decoupling and so on. So I don't really want to go too much into detail on that, but there is that quantity T2 star, which is also defined, but and is related to pure dephasing, but it's pure dephasing modulo what is called a corrective procedure, or one of them very commonly used is what is called dynamical decoupling. So I would refer people to the literature on that, and leave it at that. Thank you. Okay, so maybe I hand over to you, Prateek, now.
That's great. I can share my screen.
Mhm.
All right. So we talked about the primitives for how the memories function and what different ways of storing information in quantum information systems. Now let's talk about some operational primitives, mostly focusing on these matter-based quantum repeaters. The idea is that we use entanglement as a resource when we're trying to do quantum communications. So let's start with the basic Bell state measurements. So we are familiar with these based on quantum information courses that you might have taken. These are the four canonical Bell states that exist. So you have these correlations between the two qubits, and this is how usually it is defined. Now, these Bell states also make an orthonormal basis, such that all two qubit states can be written as a convex combination of these four Bell states. And you can use a projection of any two qubit state onto these basis states to get to get a measurement response. So if you have, let's say, a phi plus state and you measure it on this basis, you get a one. And but if you had a phi minus state, you would get a zero. Now, let's take it as a very simple example. Let's say you have this two qubit pure state in computational basis. Just as a reminder, computational basis is the native basis of a particular physical platform. So that's just as convention, we call it as a computational basis. Now, let's say we have this state get psi written as this complex combination. You can do some algebraic manipulation to write it as a linear sum of the four Bell states. Now, when we are doing the Bell state measurement, let's say we have, let's talk about simple measurements first. We have, let's say, a state ket psi, alpha ket 0 plus beta ket 1, and we are trying to measure it in the computational basis. So we can have these two measurement responses, either 1 or 0. The probability of getting a 0 is mod of alpha square, and the probability of getting a 1 is mod of beta square. Similarly, if we were to do this measurement in the x basis, so our responses could be minus or plus, we can do this some algebraic manipulation on this state to represent it as uh, some coefficient gets plus some coefficient get minus. And we can compute the probability of getting a plus or a minus by the mod of these prefactors that we were getting. If we were to perform, let's say, a Hadamard on our state and then measure it in the computational basis, 1 or 0, let's apply a Hadamard to the state that we had, alpha 0 plus beta 1. As we know that Hadamard would change ket 0 to plus and ket 1 to minus. We get these new prefactors. And then we can compute the probability of getting a 0 or getting a 1. But hey, these are the same coefficients that we were getting when we were doing a measurement in X basis. So the key idea to note from these is if you were to measure in X basis, you can also write it as applying a Hadamard onto the state and then measuring it in the computational basis. Now, why this is important? As I said, that the computational basis is also the native basis of any particular physical platform. It just makes it easier to do our measurements in computational basis, and then we can just apply some sort of a single qubit rotation onto us. As Stav mentioned, that these single qubit rotations can be done through microwave pulse or an RF pulse. So we just apply that, and then we measure in the Z basis or the computational basis if we are to measure it in the X basis. This will be useful when we are doing a Bell measurement. For a Bell measurement, the key primitive is that we have these two qubits. We apply a control knot, a two qubit gate operation, and then we measure one of the qubits in X and the other in Z. This two qubit gate operation can be done using the direct and the indirect coupling that Stav talked about. As I mentioned the previous slide, for getting this X basis measurement, you can just apply a Hadamard using, again, these RF pulses or microwave pulses, and then measuring it in the computational basis with outcomes 1, 0, 1, 0, either of these two. If we get a measurement of 0 in the first measurement result, and the second measurement result is also 0, we say that we are getting this P plus state. If we get a 0 and a 1, it corresponds to getting the psi plus Bell state. 1, 0, P minus, and 1, 1 as psi minus. So using this measurement device, we are now able to measure any two qubit state into one of these four Bell states. A quick poll question. Which of the following statements are true for the canonical Bell states? A, they form a complete basis for single qubit states. They form a complete basis for two qubit states. They can be created by using a Hadamard gate and a CNOT gate. They are separable states, and they are maximally entangled states. So majority of you answered B, C, and D. Let's look at the results. The B, C, and E. Yeah, those are the correct results. So they form a complete basis for two qubit states. They can be created by using a Hadamard and a C0 gate, and they are maximally entangled states. All right, let's go to the second. It's second primitive, and it's one of the most important primitives when we are trying to think about quantum repeaters. Is this quantum teleportation protocol? Now, you might have seen it in many of the quantum information courses. This makes the bread and butter, the crux of most of the quantum operations. So what we're doing here is we have these three qubits. We prepare a Bell state between these two qubits using a Hadamard and a control knot. And then we send one part of this Bell state to Alice and the other part to Paul. At Alice's end, we do this Bell measurement, the same device that we saw earlier, and we measure the outcomes of the two qubits that Alice is holding. The outcomes are then classically sent to Bob, and Bob applies using those classical outcomes some X and Z operations. This protocol in turn lets Alice transport the state psi onto Bob. Now, this is just using some local operations initially to prepare our Bell state, and then using these local operations to measure some classical outcomes, and then be able to apply these unitaries on Bob. And we are able to teleport this information. So local operations and classical communication. And one might even think that how do people come up with protocols like this? Quantum mechanics was discovered in 1920s, and this protocol was discovered by Charles Bennett in 1993. Charles Bennett has also been credited to develop a lot of the quantum repeater protocols. So it took, as the community, it took us about 70, 75 years to come up with stuff like this. So yeah, quantum mechanics is difficult. It takes time to come up with the real cool stuff. All right. Now, let's use the primitives that we have seen so far and understand this entanglement swapping operation. Stav briefly mentioned this in the first part of this presentation. So how do we do this entanglement swapping? Let's say we have a station Alice and the Bob, and then we have this device which is located somewhere in the middle called repeater R. Alice prepares a Bell state, and then Bob also prepares this Bell state, again using the same Hadamard and a control knot operation, and then sends one part of this Bell state from both sides onto this device R. At repeater R, we then perform the same Bell measurement circuit that we saw earlier, and then send these measurement results to one of these parties, either Alice or Bob or both. And then Alice and Bob then apply some X and Z rotations, again, single qubit rotations, to create a Bell state between Alice and Bob. It is quite similar to the quantum teleportation protocol that we saw earlier. One can even think of it as that we are teleporting an entire Bell state between parties. And this is what is called as entanglement swapping. A quick poll question: does quantum teleportation require classical communication? True or false? Let's look at the answers. Great, 91% of you believe that this is true, which is the correct answer. It does require classical communication. All right. Now let's move to the crux of the different kinds of errors that we find when we're dealing with quantum repeaters. These are primarily categorized under these two categories. One are the loss errors, and the other are operational errors. As Stav mentioned, that as the flying qubit or the photon is traveling through the fiber, it gets lost. The material in the fiber absorbs all these photons. Even when we are doing free space optical transmission, there is absorption or dispersion in the atmosphere for which we are not able to locate the photon. There are also coupling inefficiencies as these absorptive or emissive memories are interacting with the fiber, the photon emitted or absorbed or meant to be absorbed gets lost. We also have detector inefficiencies. So when we are trying to measure outcomes, when we are trying to detect the photon emitted, it might get the detectors might not function properly, or it might get lost in transit. All of these get covered under the loss errors. The other are these operational errors, which are basically the gate noise when we are trying to do either the single qubit rotations using the laser or the RF pulses or the microwave pulses. There might be some errors associated with that. There might also be measurement noise. The measurement devices might give you a faulty response. They, as Stav mentioned, there could also be memory decoherence, these relaxations and dephasing in the memory itself. And each of these interact with the system in a very different manner. Let's say we are applying this two qubit control knot operation that we were seeing in the entanglement swapping and the teleportation protocol, and there is a bit flip or an X error on the control qubit. It might lead to having an X error now on both control and the target qubit. Similarly, if we have a Z error on the target qubit, now the control and the target both will have Z errors. This is the back propagation of, this is also called the back propagation of Z errors, while the X errors propagate in a forward direction. In terms of measurement noise, let's say if we had a state ket1 and we do a computational basis measurement and we expect a 1, the measurement device might be faulty, or there might be a bit flip occurring at the measurement device itself, and then we end up reading the 0. And as we saw in earlier protocols, this correct reading of the measurement is highly critical for our protocols to function properly. Based on the different bases that we choose for measurement, it is immune to certain errors, and it is quite sensitive to other kind of error. If we are measuring in the Z basis, the X flips are critical. They end up making the measurement results completely different, while a Z error does not really affect it. This opposite is true for the X basis measurements, where the X errors do not really cause any problem, but the Z errors flip the sign from plus to minus. And we talked a bit about these memory errors with the T2 and the T1 time changing where the state resides on the block sphere or inside it. Now, when we are talking about these errors, we want to suppress these errors. And there are two basic ways of going about it. One are these near deterministic methods. So let's say we are trying to call a friend, and we are not sure about if the call quality is very good. So we tend to repeat ourselves until the friend confirms that they have received the transmission. Similarly, we can use that with information as well. So let's say if we had a ket0, we can now encode it into this kind of a repetition code, where a lot of these qubits are now sent, and this is what is called as a logical qubit. Similarly, we can do it with ket1, and there are multitudes of different ways in which you can encode information to create some sort of a logical or a higher level code or higher level of qubit. For this specific form of error correction or a specific form of encoding, it is just simple. So if you have these alpha 0 plus beta 1 state, you apply a control knot on two other qubits prepared in ket 0, and you would be able to get a state which is alpha 0 0 plus beta 1 1. So let's say we had this state and we were able to prepare the state in alpha 0 0 plus beta 1 1, and it undergoes some noisy channel, which flips one or more of these qubits. As long as we are within a certain error budget and we take this majority voting, So let's say if we had a bit flip occurring on qubit 3, and we take a majority vote, which we say that, oh, if two of them are zero, it's probably the third qubit was also zero. So we get the zero zero majority weighting or voting, and our state has now been turned to the one that we had earlier. Similarly, if we had 0, 1, 1, we would think that, oh, probably the first qubit had an error. So we apply an X rotation onto this qubit and we get this 1, 1, 1. So this is what is called as the recovery. So we had this noise and then we had some bit flips. So let's say if one of first qubit flips and we now have the state alpha 1, 1, 1, 0, 0 plus beta 0, 1, 1. Based on this majority voting criteria, we now know that we have to apply this X qubit rotation onto the first qubit. We are able to recover the state back. And for a single qubit error on state 2, on qubit 2 or on qubit 3, we are able to do the same operation again and recover the state that we had earlier. As I mentioned, this is susceptible to the error budget. If two of these qubits had flipped, we would not be able to recover the same state and end up with a different state. The probability of, however, having two bit flips is quadratically smaller. So we tend to work within these error budgets, and hence the term near deterministic. All error correcting methods have to work under a certain error budget. All right, let's take a 5-minute break here and reconvene in 5 minutes. If people have questions, feel free to write them in the chat and I'd be happy to answer them. All right. Let's start again. All right. So far we saw the generation and measurement. So we know that we have two qubits prepared in CAD0. We apply a Hadamard and then a control knot operation. We get a Bell state out of this kind of preparation. We also saw a Bell measurement where we measure one of the qubits in the X basis and the other in the computational basis. And the measurement outcomes determine what kind of Bell state that we have. Um, we also saw teleportation, where we use this Bell state preparation device, send one of the qubits to Alice, the other qubit to Bob, and then we do this Bell state measurement on the qubits that are held by Alice, the state psi, which is held, and then we use the classical and we use the measurement outcome, we send them classically and perform some unitary operations or XOZ rotations on Bob's qubit, be able to teleport the state psi to Bob's. We can use the same essential primitives now to also do entanglement swapping, which can also be thought of as teleporting a Bell state from one part to the other. All right. We saw these Bell state measurements, again, these four canonical Bell states, and then they also form an orthonormal basis. When we were talking about tools for error suppression, and we talked about the near deterministic methods using error correction, we also saw a repetition code. And now let's look into the probabilistic methods and how they differ from the near deterministic methods. So as you saw, these are the four Bell states. And let's say we are trying to prepare this state. P plus in most of the literature, at least in quantum repeaters and quantum networks, we focus on this state as a primary objective. So let's say we are trying to prepare this state and the other three states through an equiprobable, either through errors in the way we are preparing states or in gate noise or somewhere, these states are now getting prepared as well, though with a lower probability, but equiprobable for all the other three states. The probability of getting the phi plus state is f, and the others are 1 minus f by 3. This is what is called as the fidelity, and this representation is what we call as the Werner state. And this is the probability of obtaining the phi plus if we measure in this spaces. Now, um, let's think of this scenario. So we prepare two Bell states, and we send one part of the Bell state to Alice and the other part to Bob, and we do the same with the second Bell pair. So we send one to Alice, represented by the subscript over here, and the other to Bob. Now, can we use these two Bell states to improve the fidelity of the Bell pair that is, or the link between Alice and Bob? So, how do we do that? So, when these Bell states, so as I said, this one part of this Bell state is going to Alice, other to Bob. So, let's look at the Alice side. So, we have these Bell states. And then at the Bob, we have one part of this Bell state going here and the other here. Then we perform a control NOT operation and measure the other one of the Bell pairs in the Z basis. If the measurement at Alice matches the measurement at Bob, we keep the state, otherwise we discard it. And as you can see that this requires classical communication because we want to check if the measurement results at Alice also match the measurement results at Bob. Now, what is happening over here? So let's say we had a state which was in this form. So the probability of getting phi plus state is f. Probability of getting psi plus, psi minus, or phi minus is 1 minus f by 3 for all three of those. So let's say for both Alice and Bob, we have the phi plus state. So here the the superscript here talks about the first Bell pair. The superscript over here is the second Bell pair. And if both of them were phi plus, so the probability of having phi plus is f. So on this axis, we have all these different probabilities written. So we keep these states if we had a matching outcome. So the tick marks all represent if we kept the state, and the cross marks represent if we discarded the state based on these measurement outcomes. Now, not all of these states are good. So let's say if we had the phi plus state and phi plus state, that's a good scenario because that's what we wanted. We wanted to have a phi plus states at the end. If we had the phi minus state and phi minus state, which is also okay because I'll talk about it in a bit, but we essentially are able to push the kept state to phi plus. The rest of the states are false positives. So if we had a phi minus state and a phi plus state, that's a false positive. We had the opposite way, that's also false positive. And if we had the psi plus or psi minus state while we kept it, all of these are false positive outcomes. So the success probability or the new fidelity is based on if we get this state and this state, or if we get this state and this state. So if we either had both as phi minus states or both as phi plus states, that would boost the probability, that would boost the fidelity, normalized by the events that we kept. So the probabilities of getting these four states and the probability of getting these four states, and the rest we discarded. So the success probability or the normalizing probability now can be computed as f times f plus the yellow buttons. So this, and this. And the others are these four probabilities plus this one extra probability of this. So let's see. So you have f and f, so f square, then f times 1 minus f by 3 for this one, f minus 1 minus f by 3 for this one, and then the four of these elements, and then one where we had a phi minus and a phi minus on both sides. And using this, we are able to improve the fidelity of our states. When we have this phi plus, and when we had this phi minus and phi minus here, what happens is when we apply the control knot operations, the phase gets cancelled out, and the resultant state is phi plus, and you can do the math by yourself, but this is the state that we do get. Now, using this method, now we are able to improve the fidelity of this state to this new fidelity, which is f square plus 1 minus f by 3 whole square. As you can see, this is a probabilistic method because we ended up having all these false positives as well, and hence the term probabilistic. This is what we call as distillation. This particular method that I talked about is what is the Bennett protocol, or a version of it is also called as the Deutsch protocol. If you look into a lot of quantum repeater literature, this is something that you would find a lot. All right. A quick poll question based on this. Which of the following is true for entanglement distillation protocol that we introduced in the previous slides? One, it is a deterministic protocol. Two, it is used to decrease the entanglement of quantum states shared between two parties. C, it involves local operations and classical communication between two parties sharing the quantum states. D, it can convert any two qubit state to a Bell state. 88% of you said C, which is the correct answer. It does involve local operations and classical communication between two parties which are sharing the Bell state, sharing the quantum states. All right. Now let's look at some advanced link propagation schemes. One is called as encoded sorts. So this is a circuit that we saw earlier where we were doing a swap, the entanglement swapping operation. So we had the Bell states which were prepared. We send one part of the Bell state to the repeater, other part of the Bell state from Bob's side to the repeater as well. And then we do the Bell measurement at repeater. After sending the classical signals, the measurement results classically to Bob, and applying these unitary operations on the state that Bob holds, we get a Bell state distributed between Alice and Bob. We can also do this at the logical level. If you remember the logical states that we saw when we were talking about the near deterministic methods, we can also do all of these operations now on the logical level. So we prepare a logical plus state and a logical zero state at Alice, and we apply a logical C naught, which essentially would create a logical Bell state here. We do the same operation at Bob, creating a logical Bell state at Bob. We send one part of the logical Bell state to the repeater from Bob's side and from Alice's side. And then we apply a logical C naught operation and then do a logical X and a logical Z measurement. The results of these measurements would now be strings. So instead of just zeros and ones that we were getting earlier, now we would get a string of these values, which we send to Bob to apply some logical X and Z operations on the state that Bob holds, effectively creating a logical Bell state between these two parties. Now, these logical C naughts are not the most trivial thing to do. It depends a lot on the code that you are using. We also have access to some nice kinds of encoding schemes. The CSS codes, for example, allow for transversal C naughts, which is basically qubit by qubit C naught, qubit to qubit C naught operations that we can do. But this is an entire field in itself where we try to find nicer codes where we have access to nicer operations. But on a more abstract level, if we have access to these logical C naughts and logical rotations, we can do these encoded swaps and have an effective logical state prepared between Alice and Bob. Another way to look at these is if we can teleport the logical state from one part to the other. So let's say if we have this logical state psi L incoming, we prepare a logical bell state locally at the repeater. And one part of this logical bell state, we use it with the incoming psi L and apply a logical C naught operation, and then measure the received state in X basis and the state to be sent in Z basis, and use those classical outcomes to apply a unitary transformation, which ends up teleporting the psi L state uh, to the outgoing Sayal state over here. So this is just the application of the teleportation circuit that we saw earlier, but now done on a logical level. And as we will see later on, where all these different primitives get used. All right, which makes us move towards the third part of this course, architectures for matter-based quantum computers. Let's take a simple encoding scheme. Stav mentioned that light can be encoded in these different fashions. So you have these horizontal or vertical polarizations. You also have temporal modes, etc. These two polarizations is what is native to a lot of these photonic schemes. So we use the computational basis to represent this horizontal or the vertical uh, polarization. Now, when we have this, let's say we have a horizontally polarized light coming, we have this polarizing beam splitter, which is nothing but a piece of glass, two pieces of glass joined together with a dielectric. And then we have these photodiodes, which measure if a photon arrives at them. What the polarizing beam splitter does is if uh, a horizontally polarized light is coming, it sends it to one of the outgoing ports. So let's say here, this in this representation, it is sending it to the photodiode on top. If it was a vertically polarized light, it would send it to the other port. So if let's say if we have a state which is get psi alpha 0 plus beta 1, and we are measuring it in the computational basis with 1 and 0, this state is coming here. It would have a detection event at one of these two detectors, and the probability of finding a detection event would be alpha square for this, for the horizontally polarized light, and mod of beta square for the vertically polarized light. So using this beam splitter and two photodiodes, we are able to find what polarization in what polar in the quantum information stored in this photon using polarization encoding. Now, one of the things, and we briefly alluded to it in the first part of this course, is we want to we want to erase the witch path information. So, in other words, the photons that we are sending for a Bell state measurement, so essentially this device, they need to be indistinguishable. And as I mentioned earlier, there are many different properties of photons that can make them distinguishable. So you have these polarizations, spectral modes, temporal modes, arrival times. So if we have this photon which is prepared in a certain frequency, let's say we have one blue photon and the other red photon, you can distinguish them if you are to measure them in the frequency basis. Similarly, if we have, if even if both of these photons have the same frequency but a different distribution or the spectral amplitude function differs, you can still distinguish them. And this is a major problem if you're trying to interfere these photons. Arrival time is another property. So, especially when we are dealing with repeaters where we are sending photons from Alice and Bob to a station which is located in middle, we want to synchronize the time of arrival of these photons. So, if both of these photons arrive at the same time, we call it as having a good visibility, which makes good entanglement. If these have a bad overlap, so the photons do not arrive at the beam splitter at the same time, then we have poor visibility. And since photon travels so fast, even a nanosecond difference is quite huge sometimes. Now, let's try to implement a Bell state measurement in an all photonic scheme. So you have these two photons incoming, and then we have this wave plate, and we are sending it to these polarizing beam splitters that we saw earlier. If we have a detection event in uh, exactly one of these two photodiodes, or in one of these photodiodes, we get the state psi minus. So either in D2, D4 or D3, D1. If we have a joint detection in these two diodes, so a click here and a click here, and a click here and a click here, we get a psi plus state. However, if both of the photons end up in the same detector, we get this phi plus minus state. And this is very difficult to distinguish because we only have a single click event. The other two states, on the other hand, can be distinguished. So using just linear optics, we are able to get these two of the four Bell states, fundamentally limiting the success probability of Bell state measurements using linear optics. So the success probability of this is always going to be less than equal to 50%. The less than part is mostly due to these detector efficiencies and the overlap or the indistinguishability of the two photons. All right. Let's have a very quick poll question. Which of the following is true for an all photonic Bell state measurement using beam splitters and polarization encoding? A, it is probabilistic and succeeds at most 50% of the time. B, it is deterministic. C, it allows discrimination between all four Bell states. D, it is error prone if incoming photons are distinguishable. All right. So majority of you said A, C, and D. Let's look at the answer. So it is A and D. So it is probabilistic. It succeeds at most 50% of the time. And D, it is error prone if incoming photons are distinguishable. What it does not allow is discrimination between all four Bell states. So that's what we saw due to photon bunching. We are only able to distinguish two of these states. The other two states we cannot use, which also limits the success probability to at most 50%. All right. Now, with this, let's think about the different generations of repeaters as they have been, at least in the literature, this is how we have thought about the different generations of repeaters. So the one that we just saw, where we had these uh, two photons incoming and a wave plate and two of the Bell state measurement devices along with four photodiodes is what is called as a probabilistic as the zeroth generation. We still need classical communication. This is just probabilistic. We have this entanglement generation, and we are only able to mitigate these loss errors. The others where we use entanglement probabilistic entanglement generation to tackle the loss errors and the probabilistic methods to tackle operational errors give way to what is called as the first generation. We still use two-way classical communication. So we need to exchange this information for using the probabilistic methods as we saw earlier. So the distillation part and the generation part is also probabilistic. If we use some sort of error correction for operational errors, but use probabilistic methods for mitigating the loss errors, we get what is called as the second generation. And if we use error correction for correcting both loss errors and operational errors, we get the third generation. We'll go a bit detailed into all this. The key point to note is another way to look about it is this exchange of classical information. If it is two-way, all the first three generation schemes are that. So we also call them the two-way schemes. And the third generation is a one-way scheme. So all, both classical information and quantum information travel in the same direction. All right. Let's look at the two-way repeater. So you have an EPR source, two-way repeater, the zeroth generation. So you have the EPR source here and here. It is generating a Bell state in both directions, and then there is an incoming photon to the Bell state measurement device located in the middle. We get some photon detection events, which is probabilistic. So you get a 50% success probability of this. And we store the other photon in a delay line, which is basically a spool of fiber till we get the click pattern from this station both to Alice and Bob. We store these photons here in delay lines. And this is what is called as the zeroth generation. So we do not use any quantum memories, and it is just using linear optics that we are doing an entanglement swapping. If we use quantum memories, let's say we have access to emissive memories that we talked about in part one of this course. So you have the memory located on Alice and Bob, and they are emitting some photons, which is entangled to the state of these memories. And then we do the same Bell state measurement operation, which has a success probability of 50% here. If we get the correct detect patterns, we get an entanglement established between these two. This is also called as the meet in the middle design, since we are sending these photons to meet in the middle. And as I mentioned before, this requires quantum memories. We can also place an EPR source in the middle and then send photons to the two parties. And let's say if we still have emissive memories on both of these, we then send photons from the emissive memories and then do Bell state measurement at both of these stations, effectively creating an entanglement between this memory and the other memory. As you can see, if we use a scheme like this, the success probability of this is 50%, the success probability of this is 50%. So we essentially only get an overall success probability limited by 1/4. We can also use absorptive memories where we download these incoming photon directly onto the absorptive memory, but those systems tend to be limited by the cavity-based assistance that we would end up using. So it might not also be as efficient, but theoretically there is not a limit in terms of the efficiency of those cavities. This kind of a scheme is called a midpoint source design. So you have a source in the middle, and then you are sending from the midpoint to these stations. And this is the first generation of the two-way repeater schemes. We saw earlier today this advanced link propagation where we use an encoded swapping. So we prepare these logical Bell states, then we on both Alice and Bob's end, and then we send one part of this logical Bell state, and then we do a logical Bell measurement at the repeater or the station, and then we send classical outcomes to both or one of these parties to apply these unitary operations, end up getting this logical Bell state established between Alice and Bob. Let's see how that looks like. So one way to also implement it is we create this plus state here at Alice and the zero logical state here at the repeater. And we do the same thing between repeater R and Bob. And then we use some elementary Bell pairs or the elementary links to do a logical C naught. This is what is called as gate teleportation. So we are using these Bell pairs to mediate a gate operation between these two qubits. So this gate here, the logical C naught, is being implemented using these Bell pairs as intermediaries, and then we teleport this gate from this to the state that is held by the repeater. And we do the same thing between repeater and Bob. And once that happens, we have this logical bell state created between Alice and repeater and Bob. And now we can implement this logical C naught operation here but at the repeater. So locally at repeater, we apply these logical C naughts, which can be, in our case, we can use this as transversal C naughts, but on an abstract level, this is just a logical operation between this bell state and the other bell states, just like this. And then we do the measurement of this part of the bell state and this part of the bell state, similar to what is represented here. And once we communicate these measurement results to both Alice and Bob, we get this logical bell state, which is shared between Alice and Bob now. So this is what is called as the second generation or the two-way repeater schemes. Now, the schedule of swapping matters a lot. So far we saw the three two-way repeater schemes. We saw the zeroth generation, we saw the first generation, we saw the second generation. On a different note, now we are seeing how and when to do swapping when we have multiple repeaters. So let's take a scenario like this. This is what is called as swap ASAP. So whenever a link is created, let's say we want to connect Alice to Bob and we have all these different repeaters in the middle. And this link gets generated at the first time, and then this link gets generated. And whenever the other link gets generated, we do a swapping operation here, elongated this link. And at the same time, there is another link which is being generated between these two parties. And after some time, we get another link generated between these two repeaters, and then we do a swapping here. And we keep on doing that until we get a link generated between Alice and Bob. So this kind of a greedy ad hoc approach of generating links between Alice and Bob as and when they are getting ready is what is called as a swap ASAP swapping schedule. Now, one can see that this is quite exposed to the probabilistic failures. Let's say our swapping operation is not deterministic. When we apply the swapping, let's say we are using linear optics for doing our swapping, and that can fail. So if this swapping operation would have failed, we would have to be back at this space and again need to generate links between these three repeaters. So whenever there is a probabilistic failure, we go back to the zero. It's more like playing snakes and ladders, and then we end up starting the entire process again. So this is not as good when we are trying to generate links between very long distance. Can we improve it? So we can generate these links sequentially. So let's say we know that we want to generate a link between Alice and Bob, and we have also decided upon a path. So all these are different repeaters in the middle. And then Alice generates first the link between itself and the nearest repeater. We get a link over here. The next repeater generates a link to its next neighbor in the path. And then once this link is generated, we do a swap over here, and then we can keep on doing the same thing until we get a link established between Alice and Bob. Now, the distillation or other probabilistic operations can happen either at the elementary link level, or it can also happen upstream on the longer link. But as you can see that the failure probabilities are quite limited, but the risk of failure keeps on increasing, or the risk associated with failure keeps on increasing as we go downstream. So let's say if we had this link established between Alice and repeater R7 minus 1, and we do a distillation operation, which is probabilistic, and that fails, so we lose this entire link overall. So this is still better than swap ASAP in some sense, but it is still exposed to the risk of probabilistic operations quite asymmetrically as we keep on moving downstream. Now, There is another way to localize all these reset failures if we do it in a slightly more organized fashion. So let's say if we are developing these links, elementary links between Alice and Bob, and we swap at every alternate links, effectively doubling the length at all the segments in your chain. And we keep on recursively doing that until we have a link established between Alice and Bob. Now, how does this localize our failures? We let's say if we do a distillation operation at this stage, we can only fail with this half. So at most, the failure is always half of the overall risk. Uh, and if this link fails, we restart the half of this link again, while the other, if we have good memories, the other link can wait while we do this generation. And this is recursively, we can keep on applying the same principles all the way to the elementary link over here. So this nested swapping or the this is called the nested swapping schedule or the doubling scheme, and it is mitigating all these different resets or the risk of failure probabilities that we were seeing in the earlier swapping schedules. Okay, now let's move to the one-way schemes. So the one-way scheme or the third generation schemes utilizes this teleportation that we saw on the logical state. So you have this incoming psi L. You prepare a logical bell state at locally at the repeater. And then you apply this logical C naught between one part of the bell state and the incoming state. And then you do a measurement in logical measurement in X and Z basis. And based on the outcomes of that, you apply some unitary on the other part of the bell state that you had prepared, effectively teleporting this state psi L in the outgoing state. Now, usually how that works is you have this incoming state, which is missing some qubits because these photons got lost in transit. Then you apply these qubit to qubit control knot or the transversal C naught operations between the incoming block and the logical bell state that you had prepared locally, the fresh logical bell state. And once these C naught operations are done, you do these measurements on this and this block, the X and Z measurements, and based on that, you adjust the polyframe or apply the unitaries on the remaining state that you have. And this creates this now freshly prepared psi L, which can then again go back in transit. So we do this operation here at R sub 1, then some photons get lost in transit as they reach R sub 2. We do the same thing over there as well, and then keep on pushing this all the way to Bob. And as you can see, both classical and quantum information is now only traveling in this way. We do not need to exchange information back with Alice, or at least the protocol doesn't need to stop for the information exchange. And this is why these are called as one-way repeater schemes. All right, quick poll question. Which of the following generation of repeaters require only one-way classical communication? The 0th generation, 1st generation, 2nd generation, or 3rd generation? All right. So majority of you answered 3rd generation, which is the correct answer. So on the one-way classical communication is only used in 3rd generation, and hence they are called the one-way schemes. All right. As we are talking about these different architectures, one important thing is how do we measure performance? How do we know which architecture is better than the other? Well, there are a few metrics to measure the performance of these repeater architectures. Stav briefly alluded to it in part one. So we can measure the quantity of information that we transfer from one part to the other, also called throughput. We can also measure the quality of overall link that is established between a party and the other. We can also think about what it costs to generate that link between any two parties. So as we saw, all of these operations use different number of gate operations. So we have a lot of these control not operations. We all of these protocols use measurement operations. So we can start thinking in terms of the number of measurement operations that one would require, the number of qubits we would require, uh, repeaters. Not all of these different repeater architectures place repeaters at the same location. So if let's say we want to grow from New York to Boston, one scheme might require 100 repeaters and the other might just require 10 repeaters. So number of repeaters is also something that we want to see. These are all costs. Time it takes to deliver information from part A to part B. So all of these are things that we use to measure performance for repeater architectures. For one and two, we most of the literature tends to combine these two, the quantity and quality, into a single metric called secret key rate. It has cryptographic connotations, but we tend to just use this as a measure of how much information we can transfer. And it's just an easy metric that combines quantity and quality. And that's what we are going to be using uh, as we look into this performance of different architectures. All right. We saw all these different operational errors. So we have these control not operation that can be error prone. We also saw that measurement operations can also be error prone, or the memories can also undergo relaxation or dephasing. So all of these affect performance. We also saw that loss errors are critical for repeater performance. So you have this memory to fiber coupling losses, or detectors can be inefficient. All of these we take into a single metric called coupling efficiency, here denoted as eta C. A lot of literature also tends to look at all of these different loss errors separately. But for the purposes of this course, we will combine all of these together in one parameter and see how loss errors affect. Similarly, operation errors, so we gate noise that we saw earlier, so represented here by epsilon g, measurement noises, time it takes to perform a two qubit gate. So the direct and the indirect coupling method that Stav mentioned, those take time, and the time it takes might also lead to memory errors or just overall latency in the protocol. So we are also concerned about that. Memory decoherence, all of these come under operation errors. And as I mentioned in the previous slides, the number of qubits and number of repeaters are also factors that affect performance. Before we look into that, one other kind of two-way repeater that we did not talk about is this two-way repeater with multiplexing. If we have access to a lot of memories or a lot of sources, and if we can attempt elementary link generation in parallel, such that even if some of the photons get lost, we always have at least one that survive, uh, such that the probability that we would have a link between party A and party B is somewhat more than what we would have if only a single link, if we were only attempting a single link. This is what is called as 2G without encoding. So we attempt a lot of these in parallel, thought of as multiplex channels. And then we see if at least one of them survive, we consider that as a success. So let's look at performance analysis. So this is one of the seminal works done by Liang Jiang's group. Uh, so let's look at the different generations that we saw. So we saw the first generation that uses distillation to counter operational errors, here shown in these blue balls. Then we have the second generation non-encoded that uses multiplexing. In the previous slide, we saw that we were using multiplexing to uh, increase the probability of success. Then we have the second generation encoded scheme, the encoded swapping scheme that we saw earlier. And then we also saw the one-way scheme, the third generation, that uses encoding to counter both loss and operation errors. From this performance analysis, so this is for a 10,000 kilometer network, we have on this axis gate times going from 10 raised to the power minus 4 seconds all the way to a nanosecond. We have eta C, which is the coupling efficiency going from 30% all the way to 100%. And then we have gate errors ranging from 1% to 0.01%. And what we see is that for if we only have access to very poor quality hardware, the 1G is more favorable. But if when we have gate noise is reduced the poor quality hardware is here. We have gate noise, which is about 1%, and roughly it works with any sort of coupling efficiency, or it's also immune to gate times. We find that 1G is more favorable. But when we reduce the gate noise from 1% to somewhat lower, we start finding that the second generation start becoming more favorable, even when we do not have a very good coupling. So if shown here in these yellow colored spheres and the blue and the magenta colored spheres. And when we have both coupling losses are reduced, gate times are reduced, then we start seeing that the third generation or the one-way schemes start becoming more favorable. So you need a very good quality hardware for third generation or the one-way schemes to be favorable. If you only have access to poor quality, then the first generation is the most favorable scheme. All right. Let's have a quick poll question. What kind of hardware quality supports first generation architectures, but not second generation and third generation architecture? A, high quality hardware and good quality gates and coupling, good quality gates and bad coupling, C, good coupling and bad quality gates, and D, bad quality hardware, both gates and coupling. All right, let's look at results. So, um, right, so a majority of you also answered good quality gates and bad coupling. So you do not need good quality gates for 1G architecture. If you have good quality gates, second generation architectures start becoming more favorable. For 1G architectures, typically do not have that high constraint on the quality of hardware. And with increasing quality, you move from 1G to 2G and then 3G. So D is the only correct answer here. All right. We saw two-way repeaters with multiplexing where we were trying to boost the link survival probability by using multiplexing. And we saw that what happens if at least one survive, and we consider that as success. That was the second generation without encoding scheme. However, if we start looking at what happens if a lot of them survive, let's say probability that K survive of the M channels that we attempt, based on just a very simple binomial formula, we would get this kind of result. And we would find that this actually follows a very nice structure. And we can use these extra available channels to boost performance. So you have these repeaters here. You have these emissive memories that are attempting link generation in parallel. And then you have this midpoint analyzer or the Bell state analyzer array located. So some of these would have coupling losses. So these memories would not be able to generate. Some of these photons will get lost in transit. And some of them would also have the Bell state measurement not succeeding. But the ones that do succeed would end up generating a higher number of bell pairs. So in these two plots, we have, if we have access to 128 multiplex channels, we see what is the number of bell pairs that would be delivered end to end for these many number of repeaters. And all of these have are more than one for a variety of interrepeater spacing. So you always get, or there is a very high likelihood that you would get more than a single bell pair generated between Alice and Bob, which we were losing out on when we were using the second generation without encoding scheme. And this effect is more when we start using more and more multiplex channels. Another good benefit with using this is that when we are using distillation, we do not need to wait for another bell pair to be generated. Since we attempted all of these things in parallel, let's say we want to generate a higher fidelity bell pair, or we want to counter the operational losses or the operational errors that we had accumulated, we already have access to another bell pair that we can just use to do distillation. So this allows us to benefit in latency and memory decoherence if we have a protocol like this. So let's look at a fairer comparison. Let's allow third generation to the hardware that it requires to succeed. So let's give them fast gates, high coupling, low gate noise, measurement errors, and access to complex circuits, which they use for generating these high logical states. And for first generation, let's give them equal number of qubits as the third generation. So whatever logical state that we have, we use the same number of qubits here. We give them high number of memories that they require to generate these different multiplex channels in parallel. And let's also allow good quality memories for first generation. And what we see is that the two-way schemes using this kind of a multiplex two-way protocol performs better than both one-way and two-way schemes on for a variety of for almost all the parameter regime where the one-way schemes were found to be more beneficial. So in these two plots, we have 0.01% error and 0.1% error. And we also, in this paper, you can also find for a variety of different coupling efficiencies, and the results are the same. So the two-way, the 2G non-encoded way, we were using only a single link to succeed, and both one-way perform lower than the two-way schemes shown here in the black and the gray lines. And this axis is just distance for from 10 kilometers to 10,000 kilometers. The effect is the same. And the secret key rate, as I mentioned earlier, is a metric that you combine both quality and quantity. So you get better SKR performance and you get similar performance gains with even lower coupling efficiency. Now, if you are to look at the number of repeaters that are required, the two-way MTP scheme requires way less repeater than the one-way scheme again. These are on a log scale, these are the different number of repeaters. So as you can see, for moderate to high distances, you always end up using a less number of repeater than the ones that are shown here with the red dashed line. And the same also goes for two qubit gate and measurement operations. So you require less number of measurement operations and less number of two qubit gates when you're using the two-way scheme compared to the third generation and the second generation scheme. Now, we saw that the two-way MTP scheme, that the multiplex two-way protocol requires all these different memories. So memory becomes an important factor when we are looking at these two-way architecture performance. Another way is to play around with the different qualities of memories. If we combine, let's say, some repeaters with very high quality memories and some repeaters with lower quality memories, or even in the same repeater, we have access to lower quality and higher quality memories. And if we can use them by combining these two different physical platforms, can we perform better? And there's there's a very interesting piece of research, again by members of our group, who have looked into how the entanglement generation rate and coherence time. There are regions of advantages where we using this kind of a hybrid setup performs way better than just using either one quality type of memory. So in here, for 1,000 kilometer setup, the black line is what is the hybrid setting, and the blue line is when you have this type 2 memories, which are long lived, and the red lines are these lower quality memories. The benefit of using these lower quality memories are this: you also typically have access to very fast gates. So there is another dimension to this memory requirement that you have. So yeah, so using this fast and lower quality memories while in parallel with, or in association with these high quality but slow memories uh, also is quite advantageous. So what we learned is that we saw all these different generation of repeaters. We saw multiplexing. We also saw these two-way hybrid repeater schemes, and just a different way of looking at these different repeater architectures and how performance gets impacted. Uh, let's take a 5 minute break over here, and then we will continue with the different photonic and non-photonic based architectures.
All right. Okay. So let's begin the last two parts of this course. And yeah, congratulations to people who have survived the last 2 hours and 15 minutes. This will roughly be another hour, a little bit more, hour 15 minutes. Okay. So let's get into this. Till now, what we have looked at is a kind of implementation of quantum repeaters, which always uses in some way some stationary qubits, right? Apart from, for example, the zero G scheme that the zero generation scheme that Prateek mentioned. There also maybe at the end nodes you need some kind of stationary qubits, but apart from that, most of the things that were discussed from a perspective of a quantum memory based repeater, and and even the initial discussion that we had about how we envision sharing end-to-end entanglement was based on this idea that, okay, in the middle you need to divide the segments, divide the channel into multiple segments, and then these sort of gluing elements need to have some kind of uh, stationary qubits so that parallel operations can be done and then things can be glued together. But now let's sort of look at an alternative uh, proposal where the idea is that uh, can we do this end-to-end entanglement distribution just with photons, right? So if you want to eliminate completely the stationary qubits or quantum memories, is there a way that can be achieved? Okay, so first of all, let's of course ask the question of why would you want to do that, right? I mean, you have quantum memories, and there are several platforms that are already available, uh, and there is a lot of progress in that direction. But I mean, the answer to some extent, of course, is that it is an alternative proposal, and the idea is that it's more of a question of can you do this, uh, and if the technologies that enable this kind of implementation with just photons develops at a faster rate, then you would want to do that. At the same time, there could be, as Prateek was also mentioning, these hybrid schemes. Um, so there's also some merit from that point of view, that if there is some part of the quantum network that benefits from this kind of all photonic implementation, that maybe that's a good idea to think about as well. So you could have sort of these hybrid memory based and all photonic parts in a big quantum network. Everything comes together. So let's ask a question of uh, whether this quantum repeater protocol, that the type of quantum repeater protocols that we have been discussing, where you were transferring the information that was stored in the flying qubits or photons to a stationary system like a quantum memory, and then to beat the effects of loss and noise, you were doing some kind of error correction. You were either using encoded states, or you were doing distillation, which was probabilistic, but there was some kind of mechanism to correct for the loss and noise. So the question that we should really be asking is whether you can do without quantum memory is this kind of protocol where there is also some inbuilt error correction, right? So if it's just that yes, you can share entangled states end to end just using photons, which of course you can do by just putting beam splitters in the middle, right? Uh, but if that leads to so much loss and so much error that your end states take forever to create, or it has very, very low fidelity, then it doesn't make any sense, right? So the question that we really want to ask is that can we do away with memories and still implement some kind of error correction so that you get high quality, high rate states between end nodes? And the key hurdles there, essentially from the all-photonic perspective, and this is why you needed quantum memories earlier in the earlier protocols, is that 2-qubit operations in using photons are probabilistic. So you see that figure that Prateek explained just a while back, where we saw that if you wanted to do a Bell state measurement with photons using a beam splitter, a polarizing beam splitter, and beam splitters and detectors, just sort of an all optical setup, then you have at most 50% probability of success. And this is assuming that the detectors are 100% efficient, there is no other loss, there is no coupling loss, so on and so forth, right? Photons are perfectly indistinguishable and so on. So in the best case, you can get a 50% success rate. And then similarly, you will also remember from part two, where the deterministic error correction protocols were discussed, that if you want to create an encoded state, typically the encoded states that are hardest to create or the ones that are most relevant are the ones which are also entangled, right? So those entangled logical states or encoded states will also need 2-qubit gates. And we know inherently for photons, for most encodings, 2-qubit gates are probabilistic, they are not deterministic, and roughly around that 50% success probability. So if you wanted to just keep using photons to do all of the encoding operations and then your entanglement swapping and everything, at every stage, every time you put in a beam splitter, you get half of your photons are lost, right? So the rate just falls down very quickly. So to sort of address that challenge, let us first look at some background that is probably relevant here. So till now, we have looked at these Bell states, which are states which two parties share. These are maximally entangled states. And the idea of entanglement, of course, is that the measurement outcomes in particular bases for the two parties are correlated. So if you measure, say, the spin in the z basis for one particle, you get up. The other probably you might get down. But if you get down here, then there you will always get up. So there is some kind of fixed correlation between the measurement outcomes. And this is for two parties. But one can also generalize this idea to multiple parties, right? So for example, you see this triangular state, for example, right, where you have every party entangled to each other, right? But what I would also point out here is that multipartite entanglement should not be thought of just as an extension of bipartite entanglement, in the sense that it's not just a sum of bipartite entanglements. So you three-party entangled states, for example, this triangle, it does not mean that it's just that A is entangled to B is entangled to C, and A is entangled to C. That's not the way correct, probably the correct way to look at it. The best way maybe to look at it is that all three are in kind of some shared state, right? And the outcomes altogether are correlated. So for example, if you measured a very popular GHZ state, which is either all zeros or all ones, equal superposition of that, then you would see that if you measured the spin, then either all three would be measured up or all three would be measured down, right? So that's the kind of correlation that one should think of. Another example of a multipartite entangled state are what are called graph states, and these can be in general n-party states. And let us look at in a little bit more detail what those graph states are, because these will really be our resources for the all-photonic architectures. So here you see kind of a circuit diagram, right? So you have these vertices, which are plus states. So this is an equal superposition of 0 and 1. So these are individual qubits. Now, these qubits themselves, as we will see, can be either physical qubits, as in just one qubit, or these could themselves be encoded, right? So you could have a logical plus state here, right? But nonetheless, this is a plus state. And then the structure of the graph state tells you that every time you see an edge, that means a control Z operation has been done between these two qubits. So this state tells you that there is a CZ gate here, a CZ gate here, CZ, 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 and so on, right? So this lattice-like structure tells you that each vertex sits a qubit, and between the qubits that share an edge, you have done a control Z operation. And you know, a control Z operation is like an entangling operation. It's a two qubit operation. The Z operation on the second qubit depends on the state of the first qubit, so it entangles things, right? So that's where the entanglement of the graph state is coming from. All right. So this, remember, is a as we'll see, is an important resource for all photonic schemes. Okay, another small piece of background is what is known in quantum computing literature as measurement-based quantum computation. And the reason for looking at this is that this is an important motivation for all photonic schemes. So essentially, in measurement-based quantum computation, what you do is you create some kind of cluster state. What is a cluster state? A cluster state is just a graph state with a particular structure, right? If it has a lattice, if it's repeatable, it's kind of ordered, then that's typically called a cluster state. Now, this cluster state is like an error correcting code, right? So it has some error correction properties. And then if you want to do a particular kind of computation, you create a particular cluster state. Then you do some adaptive single qubit operations on the qubits in that cluster state. So remember, the important part here is that now you only need single qubit operations. So to create the cluster state, of course, you need to do these control Z gates and so on, which are 2-qubit gates. Once you have created it, you have your resource ready. And now to do your computation, once you have the resource, there is no need to do any more 2-qubit gates. Everything is just a single qubit operation. Remember, single qubit operations are easier to do. They are just these rotations on the block sphere with some using maybe some control nodes, right? For the for solid state. For photons, it's even in some sense it's probably easier. With you can do that with wave plates and so on. But now you only need to do single qubit operations. But these operations are adaptive in the sense that if you do, say, one measurement and you get a particular outcome, then you do one kind of operation. If you get the other outcome, then you do the another kind of operation, right? So there's some kind of adaptiveness in the single qubit measurements. And then once you have done the measurements and you have your outcomes, based on those outcomes, you do some kind of error detection and correction scheme. This is very similar to the encoding, decoding, recovery idea that Prateek had discussed in the previous parts. So that's how MBQC works. Now, all photonic repeaters will work more or less exactly on the same ideology, right? So you will create some encoded graph states. You will distribute those states. And here the distribution, remember, will be between repeaters, right? So this will be longer distance, right? And then you will perform some single qubit adaptive operations, right? Measurements, decoding, so on, right? So everything kind of follows the same kind of structure. There are some key differences, right? So one, as we just discussed, is that for computation, typically the distance scales that you are talking about maybe is a few meters, right? It's like a small computer in a room, right? And you don't care about distributing things over scales of hundreds of kilometers. But for communication, you really, that is the key point, right? That you want to do long distance communication. If you wanted to do just short distance, then direct communication anyways works, so you don't worry too much about it. So this is the computation versus communication difference. Communication, on the other hand, does not need a universal set of operations, right? So you don't have to do every computation, right? For example, for MBQC, there are these non-Clifford operations that are also needed as a special class of operations. Here, you don't need them. You only need Clifford operations typically, and in general, you need a smaller set of operations. So life is not difficult from all dimensions, right? Loss is the biggest threat, as we discussed, right? As soon as you start sending things more than 10 kilometers, all of this kind of the biggest problem then becomes that if you want to distribute the graph state, how much of it is it going to actually survive, right? Um, so that's a big problem. Then, because these are also going to be distributed over long distances, it will need more time. And the more time you keep quantum information in any system, the more noise accumulates, right? So even for photons, as they travel through medium, they will lose quantum information because of, say, birefringence and interactions and absorptions and so on, right? So the more the time needed to distribute states, the more noise you will incur. And then remember this, now this adaptive measurement thing is becoming more complicated, right? Because earlier, okay, you create the cluster state, you do measurement here, and then you do your operation to the next qubit or like 10 qubits away or whatever, but it's all very close by. So the classical communication cost of transferring what the outcome of this measurement to that other node is sort of negligible compared to how much time it actually takes to do the operations themselves, right? But for quantum communication, we know, as Prateek was discussing in the 0G, 1G, 2G, and the one-way, two-way sort of architectural comparisons, one of the key things to worry about really is this classical communication cost, right? That, for example, in distillation, because you have to do two-way classical communication, that is very prohibitive, right? Because while you wait for that communication to happen, everything just decays, right? Whereas in one-way schemes, because you don't have to do that, things are nice. So here we have to think about the classical communication time of adaptive measurement. All right, but having said that, this the motivation is the same, and the structure of these all photonic repeaters are exactly like measurement-based quantum computing. You create some resource state, and then once you have that resource state, you don't need to do any two-qubit operations, which were, remember, the probabilistic ones. Single-qubit operations, even for photons, typically for, say, the horizontal vertical encoding, these are all deterministic ones, and there's no sort of fundamental 50% success probability limit or so. All right. So a couple of more things that are needed to discuss the first the all photonic scheme that we have promised to discuss is a specific kind of graph state. So we looked at graph states. Remember these circuit diagram looking things, right? Each of the vertex is a plus, each edge is a gate, is a CZ gate. Now, for the all-photonic repeater scheme, you will need a specific kind of graph state. Now, of course, there are many other variants, but this is from a particular scheme by Koji Azuma and others. And this was the original work was around 2015. And they proposed this kind of specific graph state, where what you see is two kinds of qubits. So you have the red inner qubits, right? And you have the blue outer qubits. And remember, every line just means the same, CZ gate, right? So every qubit is a plus and every line is a CZ gate. The inner qubits will play the role of entanglement swapping, right? So they will be utilized to do entanglement swapping. These inner qubits are also encoded. So you see this red dot is not really just one physical qubit. Now, there can be many ways to encode this. One of the examples is a tree code. I don't want to go into detail of how that encoding works and why it works. But one of the ways to do this is to store this qubit not as a single physical qubit, but as multiple physical qubits. So this is a logical qubit, right? But nonetheless, it's some plus logical state, right? And then the leaf qubits or the outer qubits, right? So these inner qubits are also sometimes called core qubits or root qubits. And then the outer ones are typically called leaf qubits or outer qubits. And the role of the outer qubits is to actually do the entanglement generation in an heralded fashion, right? So we will talk about in detail how these tasks get accomplished, but just as a sort of preamble, you can see that this repeater graph state has two kinds of qubits. The red ones are encoded ones, so they will so they are kind of error protected, and we'll see how. and they play the role of Bell state measurement. And remember, there's some motivation to that, right? Because we said that Bell state measurements, like other 2-qubit operations, are probabilistic for photons. So by making kind of an encoded state do that business, we are trying to make sure that we can do it in some deterministic fashion, right? So this kind of graph state structure will allow you to do the Bell state measurements deterministically. And then the outer qubits are used for Heraldic entanglement generation, and as you see, there are a lot of them, and this will play a role similar to what multiplexing played in the memory-based schemes. All right. So now that we have those graph states, it's also important to know how to manipulate them. Of course, there are many ways to do that. The two most relevant rules I'll just point out. One of them is that if you take a graph state and you do a Z measurement or a Z basis measurement on one of the qubits or one of the vertices, then that essentially disconnects that vertex from the graph, right? So you go from here to here. That qubit just disappears. And of course, since you do a measurement on a qubit, the photon is lost. It's not there, and it gets disconnected. But the important point is that this edge is also lost. So it's kind of divided into now two parts. So if you think of this, the left part becomes some entangled state, and the right part becomes some entangled state. But there is no entanglement between the left and the right anymore, right? So that's an important uh, thing to know about the Z basis measurement. If you do two adjacent X basis measurements, on the other hand, so again, because you have done the measurements, the qubits will be lost, right? Those photons are gone, so they are out of the graph state. But instead of getting a disconnected state like this, you end up with a connection between the neighbors. So the neighbors end up getting connected. These things go away, but the neighbors get connected. So this is also a very important ingredient for the all-photonic protocol that we will discuss. So Z measurements will remove the edge, whereas two adjacent X measurements will remove the qubits, but will join the edge between the neighbors. So it won't remove the edge in some sense. All right. The other two kinds of measurements, which we will not use too much, but I'll just mention them because they're important, is that if you just do a single X measurement, that's also similar in some sense, that it consumes one of the qubits, of course, but then it takes the two neighbors and it joins them together into one qubit in some sense. So these are two qubits which have come together because they still have just dimension two, right? So this is just two physical qubits, but still they have only one qubit worth of information. So the edge is not lost. And then if you do just a Y measurement, then you also get this kind of situation, right? Where this qubit drops, but the edge remains. All right. So a quick poll question from the background. So which of the following is true for graph states? They are multipartite entangled states, special graph states, example, cluster states can be used to perform computation. Graph states are always one-dimensional, or all of the above. This is a multiple choice. All right. Let's maybe have the answers. Okay, so I see that most of you think that it's A and B. Okay, so they are multipartite entangled states. Special graph states can be used to perform computation. Very few think that they are always one-dimensional, and some people think that it's all of the above. Let's look at the answers. So A and B are correct. So most of you are right. No, graph states don't need to be always one-dimensional. We just saw the repeated graph states. They were two-dimensional, right? As in the coordination number was greater than 2. So they can be two-dimensional. They can be higher dimensional as well. But for our purposes, we will need 2D graph states. Okay, so now to the sort of the main part of this section, which is the operation of the all-photonic repeater chain. So now let's discuss a concrete protocol to share entanglement between Alice and Bob, where they're very far away, say a few hundreds of kilometers or thousands of kilometers, and you want to do this without the use of any quantum memories. You just have photons or photonic states, and you want to do this. And the key sort of chain of steps would be you distribute these graph states which we just discussed, right? So you have the repeater graph states, those are your resources, you distribute them, you perform some Bell state measurements. Remember, the Bell state measurements, as always, will be probabilistic. Then you do some adaptive measurement based on the success or the failures of the Bell state measurements, right? So this is again also from the MBQC point of view, that's what we have been talking about, right? Okay, so let's see how this works. So as you see, Alice and Bob, A and B, are the two people who want to share entanglement. You have two kinds of repeaters here. So this is, I mean, you could say two kinds of nodes or two kinds of repeaters here. You have the ones which have S in the superscript. These are the source nodes in some sense. And these are the ones which will generate the graph states, right? So remember, the graph state generation also needs a lot of photons, some operations between 2-qubit gates between them, and so on. And we will discuss in detail how that happens also, by the way. But let's, for example, for now, let's assume that we have that graph state with us, right? And this source station can generate them. And then the repeater stations, the ones with the superscripts are the ones that will do these Bell state measurements. So these rectangular boxes represent Bell state measurements. And so those are the two kinds of stations. M equal to 3 implies here that your graph state actually has 3 arms, right? So it has 3 leaf qubits here, and it has 3 leaf qubits on this side. So in total, it has 6 leaf qubits, 3 on the left, 3 on the right, or outer qubits. And again, remember that the inner qubits are loss protected, they are encoded, whereas the outer qubits are just one single physical qubit. So they have a much higher probability of getting lost in the channel. Okay, so having said that, now let's start with step 1. So step 1 of the protocol is that each of the source stations, for example, in this figure, C1S and C2S, they will generate the graph states. This is this GC, and 3 essentially represents the 3 leaves. And then it will distribute it in the following way. Half of the graph state will go to the left, so it will go to C1R, and half of the graph state will go to C2R on the right? So by half, I mean half of the leaf and half of the root qubits, right? So this is how it's going to happen. And then Alice and Bob are special in the sense that they will always generate Bell states, right? So these circles with a single line between them are just Bell states, right? So they will only generate 3 Bell states here and 3 Bell states there. Now, as we mentioned again earlier, let me say this again one more time, that these both of the inner qubits and outer qubits are being sent through the channel. The outer qubits are not encoded, so they are not protected against loss. A lot of them will get lost, some of them will survive. Whereas the inner qubits are loss protected because they are encoded in this kind of tree structure. So if a few of the physical qubits are also lost, the information remains. Even if some of them survive, the information remains. Okay, now what is step 2? Step 2 involves doing the Bell measurements at the repeater stations, right? Now think of this more as the heralded link generation step, right? Because essentially, if you remember in the memory-based schemes as well, that you had these 2 memories and they would emit photons, and then in the middle you would have to do some kind of beam splitter operation to create entanglement between the atoms, right? This is very similar, right? So you have these sources, A and C1, for example, right? And they are sending their photons to the middle station. This is like the meet in the middle scheme. And then you do some kind of beam splitter operation in the middle, which is the Bell state measurement. And depending on the output of the Bell state measurement, you will know whether successfully you have whether this step was successful or not, right? Whether the Bell measurement was successful or not. So based on the detector outcomes after the beam splitter, you will know whether this Bell state measurement was successful or not, right? So as we mentioned earlier, we mentioned again that this for photons, a Bell state measurement is probabilistic, at most 50% successful. So some of these will succeed and some of these will fail. So for example, here you see these 2 tick marks tell you that say these two succeeded, but the third one failed, right? Now, what you want is at least one of the qubits from these out of these three should reach from the left and from the right, right? So for example, look at the center one, right? If you get say two leaf qubits coming in from the left, but no qubit survives from the right, then you have to restart, right? Nothing is going to work. So you just restart, as in you generate your repeater graph states again, you distribute them again, and then hope that at least one survives on the left and one survives on the right for each repeater, for each of these C1R, C2R, C3R, and so on, right? And then once you get at least one from the left, one from the right, then you have to also hope that at least one of those surviving pairs, the Bell measurement is successful, right? But given that there are many of these, and here, for example, we just say m equal to 3, but these m can be 20, 30, 40, whatever, the probability of at least one reaching is very high, as in the multiplexing case. So that the formula almost remains exactly the same. There's 1 minus p to the power n, right? That's the probability that at least one of them succeeds. And then you hope that enough of them succeed so that at least one Bell measurement succeeds. Okay. So now what do you do? Once you have the Bell measurement outcomes, right? You have to do the following adaptive single qubit operations, right? Single qubit measurements now in this case, which is if a inner qubit is connected to a successful Bell measurement. So, right, for example, this blue qubit, inner qubit, is connected to a successful Bell measurement on the left, and this blue qubit is also connected to a successful Bell measurement on the right, right? But for example, this yellow qubit is connected both with a unsuccessful Bell measurement on the left and an unsuccessful on the right? And these yellow qubits, you have one success on the left and one success on the right? So the essential choice that you have to make is you have to say, okay, what are my pair of inner qubits that have successes both on the left and the right? And you choose those pairs, and on those pairs you do X measurements, right? So for example, this blue dots, you do X measurements. And remember, what does an X measurement do? An X measurement removes those qubits, but then it connects the neighbors. So it will connect these. And by association, that means that it will connect this to this and so on, right? So if you keep selecting the ones where you had at least one success on the left and one success on the right, you keep joining such successful qubits together, inner qubits together, and keep doing X measurements, they will drop, but you will get a path which connects A and B. But that is not enough, because you see that these yellow qubits are still there, right? So it's not that it's just this person connected to this person, it's these things still remain hanging almost right in the middle. And the simplest way to remove those, as we discussed earlier, is to do a Z measurement on them. Because as soon as you do a Z measurement on them, the vertex along with the edge drops, right? So this, if you do a Z measurement here and here, this entire chunk drops out from the graph state, right? And it has served its purpose, because the purpose was to allow any one success on the left for the Bell measurements, for this heralded link generation Bell measurements, to match with any one success on the right. So it didn't have to be the top and the top, it could have been the top and the middle, or the top or the below, but as long as one pair survives, you are good to go. And everything else you just drop out. Okay, so this was step 3. And then finally, now nothing remains to be done, but just to show you how this works is that, for example, here you had this pair successful Bell measurement. So you had done your X measurements on these things, and sorry for the color code. These should have been blue, but I guess you you know what I mean here now. That these are all X measurements. These are the successful ones, and then you have these two successes here. So you do X measurements here. So if you get one yellow path, right, from A to B, then you have, after doing the X measurement, an entangled state between A, which is this qubit, so the top qubit of A, and the middle qubit of B, right? For example, in this case, right? So the X measurements allow you to keep the edge, removing the vertices, but the Z completely sort of removes the vertex as well as the edge, so it disconnects those parts of the graph state. So I see we did not use any quantum memories. This was all photons. This graph state is photon. These Bell measurements are all photonic. These Bell states are also photons. And doing that in an error protected way, you were able to generate entanglement between Alice and Bob. And there were two crucial points here. One was the fact that the inner qubits are loss protected, right? And these are the ones that allow you to match the left and the right, right? So anyone on the left can be matched with anyone on the right because of this sort of mesh-like structure in between. So that's where the graph states sort of resource comes in, that because of this kind of multipartite entanglement structure, it's not like you have one link here, one link in the middle, and one link in the bottom, like you would have in multiplexing. It's a mesh structure. And the other one was that because you have many arms, you have heralded entanglement generation. You hope that at least one of these arms will be successful, right? So there is no real heralding happening. Just to point out that you don't tell anyone about anything, right? Because there's no option of waiting. Everything happens at the same time, right? Photons just fly out. You do all your Bell state measurements. You do all your adaptive operations in one go, right? That's it. Okay. So now let's and the only classical communication is for the sort of adaptive thing is happening locally, if you also see, right, that this Bell measurement, if it succeeds here, it only has to communicate to this inner qubit and nobody else, right? That you have to do an X measurement here, and by extension, every place there where you don't do a X measurement, you do a Z measurement. Okay. So a few more sort of points about this scheme, which are relevant, is that X and Z measurements, remember, we are also doing only on the inner qubits, and that's by design in some sense. That you know that the inner qubits are noise protected and they're also loss protected, as in they can be encoded by this, say, for example, this tree code. Even if some of those are lost when they are sent to the repeaters on the left and the right, you will be able to do your X and Z measurements successfully by using the remaining physical qubits. Right? So, for example, in this tree, you start by doing measurements on the leaf qubits. If one of them is available, then the measurement outcomes on these leaf qubits tell you the measurement outcome of the root qubit automatically. You don't have to do all the measurements. If these are lost, then you go to level 1. If that is lost, you go to level 0, and so on. Right? So you have multiple chances to measure the X and the Z outcomes correctly using this encoding. So this not only protects you against loss, it also protects you against noise, because if you measure many of them by sort of accumulating the information of those measurement outcomes like you do in recovery, you can tell whether an error has occurred or not. So for example, this X measurement, if it had flipped, right, it is highly unlikely that it will flip for all of these physical qubits, right? It might flip for one or two of them, but it's highly unlikely that it would have flipped for all of them. So by looking at the stabilizers of that code, you will be able to say what the correct X outcome or the correct Z outcome is. Now, another very important point here is that even though this can tolerate loss and noise both, it cannot tolerate infinite loss, right? Or if a very high percentage of photons are lost, then you cannot recover things. So very much like the bit flip noise, for example, if you have more than 50% noise or more than a 50% probability of your bit flipping, then no matter what code you use, it's not going to correct that bit flip. right? In the same way, if you have more than 50% loss, there is no code that you can implement here that will be able to recover the logical information of this inner qubit. So that's a hard limit, and this comes from the no cloning theorem. I wouldn't go too much into that detail, but essentially, if you have more than 50% loss in your channels, then none of this is going to work. The encoding is not going to work. So that puts a hard limit. And remember that 50% loss is not a big deal for fiber optic cables, right? You get 50% loss very quickly. You get, say, in 15 kilometers or 20 kilometers, you get a loss of factor of E, right? That's more than 50%. So, uh, so the repeaters, they cannot be spaced out too far in this case, because loss is really the noise that you are worrying about here, right? The error that you are most worried about here is loss. uh, so if you get more than 50% loss, then the entire scheme falls. So your repeater spacing cannot be more than say tens of kilometers. But still, you don't need any memories, so it's only photon sources. So probably you can put repeaters every 10 kilometers and be happy. And one more small point is that depending on the application, A and B, the end nodes might actually need memories, right? Because if they want to use it for some other operation, maybe they want to collect 10 entangled states and then want to do something, or they want to utilize it. They have to wait for some input state to come, which they have to teleport using that entangled state. Depending on the operation, on the application that you have in mind, A and B might actually need memories, but that's really not part of the repeater protocol in some sense. The task of the repeater is to distribute entanglement between A and B, um, and that it can do without using any quantum memories. And one quick point that I would also like to mention, which is talked about often in literature about these all-photonic schemes, is that they're time reversed in some sense. And the reason people say that is because in a typical memory-based scheme, you would do your heralded link generation first, right? And then you would do your entanglement swapping. Here it's kind of reverse in the sense that the entanglement swapping is already done for you in the repeater graph state, right? You're not doing any swaps amongst the successful links. That's inbuilt by this kind of mesh structure. You're doing some single qubit measurements, but that's just to kind of reveal the structure. It's not uh, sort of implementing it. It's already pre-implemented in the resource state. But the heralded link generation is happening after that. So the heralded link generation is happening when you do these Bell measurements. You know which of the arms succeeded, which of the node level links actually appear, right? So the path gets selected later. So that's the sense in which people call it a time reversed protocol. Okay, so briefly again, this because there were a lot of steps and a lots of points. Just briefly revising the steps. You had the generation of the repeater graph states at the source stations. You distribute half to the left, half to the right. Then you had these Bell state measurements, which are associated with the heralded link generation part of the protocol. Some of these succeed, some of these fail. You hope that at least one uh, leaf qubit arrives and at least one Bell measurement succeeds at each repeater. Then, depending on the success or the failure of the Bell measurements, you do either X or Z measurements on the inner qubits. The inner qubit measurements are loss and noise protected because they're encoded, and that allows you to choose a path. And this path ultimately tells you that there is these all of the yellow qubits will drop out, and you will have entanglement between Alice and Bob. That's end-to-end entanglement. Okay, so that was a sort of long discussion about the all-photonic protocol, and this is one of the protocols, but it's one of the first and the most relevant and has all the essential details. So let's do a poll question now. All-photonic repeater chain that we just discussed with the work by Azuma uses repeater graph states for which of the following purposes? And this is also a this is I think it's a single choice. Yes. All right. Let's see what people think about The answers, I see most of you think it's all of the above. So what is all of the above? It's you have to perform uh, entanglement swapping deterministically, perform heralded entanglement generation between neighboring nodes, and provide resilience against photon loss. So yes, all of the above is the correct answer. So everybody who selected the other options was also right, partly. But this is each of the things in the repeater graph state really plays one role. So if C performed entanglement swapping deterministically, we just discussed that the inner qubits and the mesh structure or the graph state structure between them plays the role here that allows you to do swapping deterministically. And then the heralded entanglement generation is allowed by those multiple leaf arms that you have. And this also provides automatically resilience against photon loss, both for the leaf qubits and for the encoded inner qubits. All right. So we have discussed all photonic architectures, why we need them, what can you do to implement them. But we have left out till now a key element, which is how to generate those repeater graph states, right? Because that's the real resource. That's where that deterministic entanglement swapping, which was the key hurdle, uh, that ability is coming from. So let's think a little bit about how to generate repeater graph states. And I will here again give you a sort of broad view of the generation process. There are very many specific details about these things that are beyond the scope of this small course. Okay, so two main steps. You generate some small unit resource. So this can be some small entangled state. This can be a three-party GHZ state, a Bell state simply, so on, right? Or a GKP state like in the continuous variable encoding schemes. You generate some unit resource, and then you stitch them together to generate this graph state, right? So that's the philosophy. You can do this both in an all photonic way, right? So then that makes this a all photonic architecture, right? So both the generation of the resource and the implementation of the repeater schemes have been done photonically. The problem, of course, with that is that, again, you will need these entangling operations, right? And remember, entangling operations for, say, polarization basis is 50%, has a maximum success rate of 50%. Whereas in some other implementations, the two-qubit gates themselves or the entangling operations themselves might be deterministic, but the resource preparation itself, like the creation of that unit resource, that itself is probabilistic, for example, in the GKP states. You can also do a sort of hybrid business, right? That you use matter-based uh, uh, platforms to generate the repeater graph state. But once you have the repeater graph state, you do the Azuma protocol, for example, right? Everything is all photonic. There is no more memory business. You have some emitters or some matter-based platforms that allow you to generate the graph state, but that's the role that they play. Okay, so that is okay. You generate some Bell state. Maybe you have the simple SPDC source, right, to generate the Bell state. So that's not really the difficult part. The difficult part is how do you stitch those unit resources together. And to this end, there are two very popular schemes. One is what is called type 1 fusion, and the other one, of course, type 2 fusion, right? So for type 1 fusion, you take a beam splitter. It's a polarizing beam splitter, so it discriminates between horizontal and vertical polarizations. You put your two ends of the cluster state into it. So, for example, think of this figure A. You have a cluster state on the left and you have cluster state on the right. You put the right end of one cluster state and the left end of the other cluster state into this beam splitter, right? And once you have the output, you measure one of the photons that come out in the X basis and the other one you just let it go, right? It just sort of flies away. It's no more part of the cluster state. If you get a particular kind of measurement outcome, then it turns out that you have successfully joined the two cluster states. So if you see, as you can see from the newsletter, you did not do any measurement on one of the qubits. It was also completely lost. You kind of end up joining these two qubits together and you get a fused cluster state. So you get a longer cluster state, right? That's when things are successful. Similarly, if you had two linear cluster states like this, right, as you did a fusion operation between the middle ones, then you can also generate a 2D cluster state like this, right? Because these two things get fused together, right? So this is almost like doing a single X measurement, right? Remember, this is what a single X measurement was doing. It was putting those two qubits together into one qubit in some sense. But type 1 is not really very good for 2D clusters. So for linear clusters, it's fine, even if you fail. So just concentrate, for example, on the top part of the figure. So if you fail, then that qubit just drops off and the thing gets disconnected, which is fine, right? I mean, it was never connected to begin with because with the linear ones, when you were trying to join, they were not connected. The qubit drops out. You have one less qubit, but okay, all right, it's not too bad. But when you are trying to connect two linear cluster states and you do type 1 fusion and it fails, then, which is 50% of the time, then you end up with this scenario where not only do these that the joining operation fail, but both of the linear cluster states also become size half, right? So all the hard work that you had done to generate that long cluster state kind of goes up by a factor of 2, right? Because you again end up with two half-length cluster states, both on the top and the bottom. So this failure is very much like a Z measurement. The qubits drop out and the neighboring connections also drop out, right? So therefore, type 1, although is a simple and a nice scheme, it's not the best scheme to generate 2D cluster states. Okay, so now what does type 2 fusion do? Type 2 fusion is also very similar, but here what you end up doing is you use a polarizing beam splitter which discriminates between the plus and the minus polarizations. And at the end, instead of measuring just one of the photons in the X spaces, you measure both of the photons in the X spaces, right? So you measure both of the photons in the X spaces. And here what happens is now when you try to create a two-dimensional graph state, if you succeed, which is this pathway from A to C1, then you see that things are very much similar to the type 1 situation, right? You do a single X measurement that fuses two of the qubits, and then you do one more X measurement that just joins the top uh, cluster state to the bottom cluster state, and you get a 2D state. So all good. Then you have to do some adaptive measurements and so on, but that's roughly the scheme. But if you fail, now you see that it just you lose one qubit from the top, you lose one qubit from the bottom, but you don't lose the connections. So it doesn't chop off the linear cluster states even in the case of failure. And that's a good thing. Because if you have spent a lot of time and energy creating a long cluster state, you don't want to chop it off into two or three or more parts, depending on what kind of 2D state you are trying to create. So another example, you could think of this thing, this more complicated thing. So now think of exactly that point, right? That if you ended up chopping up these linear cluster states every time you fail, you will end up with very small, lots of small bits. Not the best idea, right? And recall that the idea that we started with is you wanted to generate this kind of 2D cluster state, right? So 2D cluster states are really important, and type 2 fusion, therefore, is really very important to do this scheme. So for 1D parts of the thing, you can still use type 1, but then when you want to fuse linear cluster states together to get a 2D state, typically you would do type 2 fusion. Okay, a quick poll question. Which of the following are true for type 2 fusion? It is a deterministic process. It can be used to stitch together two cluster states. It uses Z measurement of one qubit. It uses X measurement of two qubits. All right. So, okay, many people think that it's a deterministic process. Okay, that's not true. It can be used to stitch together two cluster states. That's absolutely true. Uses Z measurement of one qubit. No, that's so type 1 fusion uses measurement on one qubit, and that also is not a Z measurement. And then for type 2, you have X measurement of two qubits, which is correct. Let's see, the correct options are B and D. All right. Prateek, by the way, are there any questions in the chat or
Uh, there are no questions.
there are no questions? Good, good. Okay. All right. I hope people haven't fallen asleep. Okay. So now that we have looked at the sort of photonic way of generating graph states using type 1 and type 2 fusion, let's also look at the deterministic way. And remember, as we mentioned, everything that involves beam splitters and photons is typically probabilistic. So type 1, type 2 fusion are also probabilistic. You have success, you have failure. But there is also a deterministic way to generate these things, and that uses emitters or matter-based platforms. So one of the schemes to do this is very, very similar to the emissive memories that we discussed earlier, that you have these two ground levels, right? The lower solid black lines, and you have these two excited levels that are the dotted lines. You send in a pi pulse, which is linearly polarized. So it has the left circular and the right circular polarization in equal parts. You send it in, and that excites both of the levels. And when the levels come down, depending on which level the atom decays to, whether it decays to the left or it decays to the right, the output photon will either be left circularly polarized or right circularly polarized. So then you can call it the zero state of the new photon or the one state of the new photon. And the spin again also will be either in the left state or in the right state, zero or one, but there will be a correlation. So if it decayed to the right state, then the output photon will be right circularly polarized. Whereas if it went to the one state, the atom went to the one state, then the output photon would be left circularly polarized. So this is exactly like doing a CNOT gate between the spin, which is this atom, and the new photon that is coming out, right? So this is like a control NOT gate, and therefore it creates entanglement between the spin and the photon. This is what Prateek also mentioned, that to create entanglement, you do a Hadamard and a CNOT, and that's what does it, right? So this creates the atom photon entanglement. And now if you keep on doing this repeatedly, right? So you have that electron spin, you did a Hadamard, you do a C naught, you do another Hadamard, you do another C naught, another photon comes out, you do a Hadamard, another C naught, another photon comes out. So you keep generating photons out of the same atom or the same spin. And each of them, because they are generated from the same atom, are not only entangled with the atom, but they are also entangled to each other, right? So you get that linear cluster state structure that you wanted, right? That by repeatedly throwing this pi pulse onto the emitter, and every time a new photon comes out, it's entangled to the other photons and the emitted and the emitter itself. Okay, so that's a nice scheme. Now you can generate two-dimensional graph states also using this kind of structure. And the idea there is that by sort of switching the Hadamard gate from the new photon to the spin, right? So either you do the Hadamard gate on the new photon, or you do the Hadamard gate on the spin. Depending on that, the either the new photon becomes a leaf or the spin becomes a leaf of the linear graph state, right? And of this kind of, not a linear graph state, but sort of this long graph state that you have. And using this kind of switching, you can generate what are called these caterpillar states, right? So these are these kind of very long cluster states with spokes coming out of them at every node, right? And it has been shown in this paper specifically, that once you generate a class of these caterpillar states by fusing them together. So now remember, you can send, say, for example, one photon that is from this caterpillar state, and you can take another caterpillar state, and you can take that one photon from that state, send it through a beam splitter, do X measurements on both of them, which is type 2 fusion, and generate a 2D cluster state. Right? So that part, of course, will be probabilistic, but then this linear cluster state generation or this sort of caterpillar state generation can be deterministic, but that part can be the fusion part can be non-deterministic. On the other hand, there are other schemes where you use emitters and other physical or other sort of memory systems, which are called ancilla systems in that case, which have much larger coherence times than the emitters themselves. And by using these multiple emitters, you can actually generate the 2D cluster state directly without having to generate first these caterpillar-like states and then fuse them together. So there are many, many sort of ways of generating these cluster states, and this is a very rich field of work in itself. How to efficiently generate, what would be the minimum number of emitters that you would need to generate a graph state of a certain size, uh, how many fusions would you have to do, how to optimize those fusion operations, because each of them is probabilistic, let's say. Even if they are not probabilistic, different using multiple memories or multiple emitters or ancilla systems introduces noise by decoherence, right? And every time you do a C0 gate, there is more noise. So you want to optimize all of those things, and this is a wonderful sort of field in itself, which has a lot of progress recently. Okay, so now we move to the last part of this course. And here we would just sort of briefly compare the different photonic architectures that we have, the photonic architectures that we have, and a little bit to the matter-based schemes as well that we had discussed. So let's do that. So let's first try to do a very sort of coarse estimation of what would be the end-to-end rate of entanglement for this Azuma scheme that we just discussed, right? And this is a very sort of rough estimate. So this would work for most kind of repeater chains based on the all-photonic scheme, but it will also sort of underestimate a lot of the details. But this is just to give you a sense of how these estimates are made. So the first thing you remember, the step one was to generate the graph state, right? And that itself takes time, because we saw all this complicated business of type 1 fusion, type 2 fusion, emitter-based schemes, so on, require some time to do these operations, right? So there is a rate at which you can do this. There's a trial rate at which you can generate these graph states. And that rate becomes sort of your rate determining step for the protocol, right? So this will give you the time step for your, so as to say, of your protocol, right? That's the minimum time needed to repeat the protocol. Then once you have generated the graph state, half of it has to be distributed to the left, half of it has to be distributed to the right, right? So for each arm, you will, so this refers to the 3 or 4 arms that we had, the 3 arms that we had in the Azuma scheme, if you remember in the discussion that we did. You have these multiple arms. For each arm, you would have the success probability of the photon actually reaching the beam splitters, right, for the heralded link generation. And you would have coupling losses, you would have the losses associated with the single photon generation, the graph state generation itself, and so on. And all of that put together will give you a success probability, which is the product of the beam splitter, the Bell state measurement operation that happens in that arm. So this can, for example, at most be 50%, but it will probably be less. And then the square of the link success probability, right? Because you have 2 coming in, one from the left and one from the right. But as we discussed, you need only one of these arms to succeed for each segment, right? You don't need all of them to succeed. So then the probability that at least one of them succeeds is very much like the multiplexing case, which is exactly like the multiplexing case, and you get this. So if the success probability of one arm is this, then at least one arm succeeding. If you have m arms, the probability is this. But now you want one arm to succeed in each segment, right? So now it's not an or, it has to succeed in each of the segment. So then the probability kind of goes down by a factor of, n minus 1, right? So the probability becomes this factor to the power n minus 1. And that multiplied by the sort of base rate, right? So this is the rate at which you can repeat the protocol. So you multiply all of these things together, you get a rate estimate, right? And this is a rough estimate, but it tells you what are sort of the key elements, right? So if you have a lot of loss in the channels, then your rate is going to go down. If your generation of the graph state is very slow, I'm sorry, then the rate goes down. If you have many, many arms, then the rate goes up, right? So if you have a large cluster state, then the rate goes up. But if you have many, many segments, then the rate goes down, right? In that sense, that you have that n minus one factor here. But remember that for a fixed distance, if you increase the number of segments, then the length of each segment goes down, and then probably this eta link will go up. So this lets you play that game. This kind of rough estimate lets you play this game and see where you are in terms of the rate. For example, for the Azuma scheme in the original paper, also they made some estimates that were much more complicated than the estimate we just talked about, but kind of works on the same principles. And they saw that if you have a 5,000 kilometer distance between Alice and Bob, and you place repeaters every 4 kilometers, so remember this 50% loss problem. So if you remember from Prateek's part of the talk for for memory-based things, you could place repeaters even 100 kilometers apart, right? But here you cannot do more than a few kilometers. So, for example, in this case, they said 4 kilometers. You had a photon source rate of 100 kilohertz. So this is like your resource that generates your graph state, right? And you had 24 arms, right? So you had m equal to 24. Then the end-to-end rate that you would get is 69 kilohertz, which is comparable to your source rate. So that's a good outcome. And the number of photons that you would consume is of the order of 10 to the power 7, right? So that's a lot of photons, single photons that you have to consume to get this to this high rate end to end. And you get a fidelity of almost 90%, which is good. In comparison, if you were using direct transmission and you had, instead of 100 kilohertz, a 10 gigahertz source, which is a really, really, really good source, then to send one photon from Alice to Bob with a distance of 5,000 kilometers, it would take roughly 175 years to do that. So all of this is sort of to say that, yes, there are a lot of challenges in the all-photonic scheme, but the flip side is that if you are successful, you will be able to solve a problem which otherwise does not have a solution. And then let's quickly talk also about sort of this trade-off between performance and resource requirements. So as you will see, as the Azuma paper already showed, and there were other works later on that showed that the total number of photons which are consumed, like we saw this 10 to the power 7 number that we talked about, actually grows polynomially with the distance. So it doesn't grow exponentially with the distance. So that's a good thing, but it still grows polynomially with the distance. So as you go to longer and longer distances, you will need bigger and bigger photon sources. And the average rate end to end, as we saw in this calculation, kind of depends on the weakest factor, right? So if this thing, the repetition rate is the slowest factor, then that gives you a sort of a estimate of your rate. If it's the detectors that are slow, if it's the classical communication feed forward, remember even within the node you had to do some kind of classical communication. If that takes time, all of those things will determine your average rate. For emitter-based schemes, for example, the CZ gate that you have to do also takes time, and that sometimes becomes the slowest step. If you are using a single cable or a single optical fiber and you want to have m equal to 24, that typically means that you have to use different wavelengths for each of the arms. And that puts you in a bandwidth problem, right? So you cannot put infinite arms in a single optical fiber, or you have sort of parallel fibers for each thing, which is also not resource efficient. And then, as we discussed, this internode separation is a thing that you have to care about because of this 50% loss limit. So you need a lot of repeaters in the all-photonic scheme. So for 5,000 kilometers, if you put one every 10 kilometers, then you need 500 repeaters. So that factor n is 500. All right. Some other schemes, there is this one-way all-photonic repeater chain scheme as well. Prateek already discussed it to a matter-based analog of this, so I will not focus too much on this. You can sort of generate this repeater graph state and then keep teleporting it forward. So you have only one-way classical communication, keep teleporting it forward. And the resource that gets consumed is a logical Bell state, which in this case, instead of like some other encoding that one would use in the memory-based scheme, here the logical state would be the repeated graph state. So you have a Bell state, each of whose like A and B, both of them are repeated graph states themselves. So you use this logical Bell state to teleport forward the graph state, and that gives you error correction. In terms of performance, the only sort of key points that I would like to highlight are the fact that if you look at the transmission efficiency, or this is proportional to the rate that you get end to end, you see that for distances over 100 kilometers on the x-axis, the blue and the red lines or the orange lines do much better than the black line. The black line is direct communication or the plop bound, whereas the blue and the orange lines are the ones with the all-photonic scheme for different memory, for different repeater efficiencies. So this includes your single photon generation efficiency, coupling efficiency, and so on. And if you use larger codes, then of course you get better outcomes. The other thing that I would like to mention is also that the internode separation, or the number of repeaters that you need per kilometer, also grows with the total distance, because you have more loss and more noise. It's not that as you grow the distance, you can still keep repeaters 4 kilometers apart. If you have a distance of 5,000 kilometers instead of 1,000 kilometers, then you probably have to also space your repeaters closer together, which puts an additional resource cost. There are other schemes also which are very similar to the hybrid scheme that we also discussed in part 3, where you can combine these continuous variable and discrete variable systems together. The idea is that the discrete variable, the continuous variable system itself has some very nice photon loss resistance inbuilt into it. So you can base one kind of repeaters on that. And then every few hops, you can sort of concatenate a lot of these continuous variable states into a discrete code or a discrete variable logical state to get rid of more errors. And here also the sort of results are very similar, so I'll sort of gloss over that. That for longer distances, you see that the all-photonic scheme wins. Okay, so one final thing is the comparison between matter-based and all-photonic architectures, and you see that the main bottlenecks are typically different. That for matter-based schemes, because everything is sort of relying on that quantum memory, you want very high coherence times and you want very low gate errors. Whereas for the all-photonic scheme, it's really photon loss, which is your biggest problem, and the probabilistic gates that you keep and have to do when you generate the graph states, when you do the heralded entanglement generation, and so on. So the scaling in that sense is also determined in the matter-based scheme by the classical communication time and sort of its relation with the coherence time. So time is really what sort of bounds you. Whereas in the photonic case, it's really because there is not much classical communication that you have to do at all in any way. It's really the photon resources that are the most that scale really badly, and in some sense, and that stop you from extending the system. So the favorable regimes, of course, then is that if you have very long distances and you don't have a very high repetition rate for your photon source, then you should choose matter-based schemes, get a very good memory, and do things sort of asynchronously. If you have a very high repetition rate source and you are thinking about a few hundred kilometers so that you don't have to put, say, 10,000 repeaters, then you should think photonic. The key benefits then also related to that is that for matter-based schemes, you typically need fewer resources, but you need very good resources. Whereas for the photonic schemes, you probably don't need all of those memory qubits. You don't need any cryogenics. Photon sources are typically easier to handle, but you need a lot of them. All right. There are many, many, many other schemes. This is just to show that this is a rich field, and people have compared things to each other, and there's a lot of literature on that. Okay, so final poll question: can all photonic architectures beat the performance of matter-based quantum repeater architecture? right, let's see what people think about this. All right, wonderful. People think that it's complicated, and yes, it is. So I think I have been able to communicate that there is a trade-off. Yes, it's there are some regimes in which one is better, and other regimes the other is better, and probably hybridization is a very good way to look at this. So quickly in the last 1 minute, I hope that we were able to convey why quantum repeaters are needed, what they are, and how they function. Those were the three things that we were hoping to convey. In the first part, we looked at physical primitives. In part four, we also looked at photonic state primitives, how they are physically generated. Prateek talked about operational primitives and all of the protocols that sort of form the core elements of all quantum network architectures. Then we moved on to architectures. We looked at the simplest ones, just based on beam splitters. We went to multiplexing, distillation based things, error corrected ones, one-way communication, then finally to all photonic schemes. And we also tried to do a performance comparison, and we finally came to the conclusion that each of these schemes have their own regimes of benefit, and probably one should sort of think of the trade-offs that are involved and the resources that one has before deciding which scheme to choose. And I hope if we were able to convey that, uh, I would be happy. All right. So that's the punchline. That quantum repeater based architectures with direct communication over long distances, but they need more resources. So probably hybrid architectures can reduce the resource requirements. Thank you. Are there any questions in the chat, Prateek? I can't see it, but I can also, I think. About.
There was a question about the technology that PsiQuantum is currently using.
Uh-huh. I mean, yeah, they have a all-photonic way of doing computation. So yeah, they definitely use a lot of these type 1, type 2 fusions that we discussed about. Graph states are also very important for computation. So this is very similar to this all-photonic motivation. Yes, but exactly, they are more focused on computation. All right, so maybe I should stop sharing because yeah, we are out of time as well.
Sweet. Thank you guys so much for joining us today. Appreciate
Thank
it.
you, everyone. Thanks.
Thank you,
Bye-bye.
everyone.